Okay, yes, recording in progress. Fine. My name is Stefano de Gironcoli. I will talk this first part of this lecture about forces, stress, so basically derivatives of the energy and how these are used for structural optimization. In the second part of this lecture, Anton Kokalj will talk about NEB and will explain better what NEB is. Okay, so let me advance. Forces. So we have learned how to calculate energies and how to make the calculation converge with respect to cutoff and key points and asking for sufficient self-consistency. And one byproduct of a SCF calculation is that we have the wave functions of the amplitude of the system. And one nice thing that happens in a plane wave formalism is that derivatives of the total energy with respect to external parameters are easy or not too difficult to compute. Forces are derivatives of the total energy with respect to the atomic position. And as far as the electronic problem is concerned, atomic positions are external parameters. So forces are computable. Stress is a similar first derivative of the energy because it's the derivative of the energy with respect to deformation. So position of the atoms can be varied, and this gives access to forces. The shape of the cell can be varied, and this give access to stresses. And with forces and stresses, one can then make a variation. I mean, one can evolve the system and basically to search for the best geometry, the best internal coordinates, or the best shape of the unit cell. So there are basically two strategies. One is basically use the force and the stresses to evolve the system with a final step method. And for instance, steepest descent, you just calculate the derivative, so the direction of largest variation for the energy with respect to atomic position, and you follow the gradient, well, the negative of the gradient over the minimum, or actually you do this basically implementing Newtonian dynamics and evolve the system in a dynamical way, but you add a friction terms that therefore withdraw kinetic energy from the system as it evolves, and then eventually it will arrive at a minimum where the forces are zero. And this is implemented via an algorithm that is called QuickMean. There are more sophisticated methods in which you don't do this by step with a small step. So these dynamical methods, let's say, typically are done using a small final step which remain constant during the evolution. There are other methods that may be more efficient, like conjugate gradient or quasi-Newton methods. The FGS is the name of an acronym of a method to implement quasi-Newton minimization, which kind of try to go beyond this fixed time step, finite time step method, but they choose some minimization direction, and in that direction they try to guess the right step size to to reach the minimum, and then they choose another direction, and so on and so forth until. So this should be more efficient. We will see that in some situations they are indeed more efficient, but for certain, when you start far from the minimum, they might be the simpler steepest descent damp dynamics strategy may be more efficient. And all these apply naturally to forces. If you want to change the cell shape, it's a bit more complicated. You need to have access to stresses, and there is this variable cell shape dynamics or variable cell shape relaxation that require a little bit more theory, but not particularly much. But we will discuss this later in this presentation. Okay, so let me proceed. Okay, so the idea that forces are easy to compute in a plane wave basis set is based on the Hellman-Feynman theorem. Hellman-Feynman theorem is an important theorem that states that if you are in presence of a variational principle, as we are, the density functional theory yesterday introduced by Paolo Giannozzi is a formalism in which the electronic problem is seen as the minimum of a functional with respect to variation of the density or the Kohn-Sham wave functions. So when you have a variational principle and this gives us a functional, the energy in our case, as a function of variables, external variables, the atomic position or the atomic shape or the cell shape in our case, this energy is obtained as a minimization problem. And then the derivative of this energy with respect to this variational object with respect to its these parameters, the position, in principle should contain variation derivatives, explicit derivative of all the terms. Now, the energy is the expectation value of the Hamiltonian with respect to the wave function. The wave function, when we minimize it, we minimize the problem, is the ground state wave function. And so, in principle, we would have terms containing variation of the Hamiltonian, of course, but also of the wave functions. When we change the position of the ions, the variational best wave function for the problem will vary. So this term would be complicated. Would require an additional SCF calculation to calculate how much the wave function change when you change the position of the atoms. And indeed, this is what is done to calculate the vibration properties, so the phonon cause that you will discuss tomorrow. But the nice thing of the Hellman-Feynman theorem is that the first variation of the wave function does not enter in the first order derivative, because by the variational properties, the contribution, the order variation does not contribute to the first order variation of the wave function does not contribute to the first order direction of the functional. It is the condition of being at the minimum is automatically imply that the contribution of the variation of the wave function comes out. And so the energy, the derivative of the force, the force is the derivative of the energy, but this derivative of the energy can be computed knowing how the Hamiltonian vary. This is kind of needed, but this is something that we can explicitly compute, and keeping and calculating the expectation value of this quantity on the ground state wave function, on the self-consistent solution that we determine at the end of the SCF calculation that we saw yesterday. So and explicitly one find out that if you were to write the force and analyze how this derivative of the electronic energy is expressed, this in the end is nothing but what you would expect from a classical picture in which you have electrons that have a certain distribution, and they interact with the nuclei with the Coulomb interaction, and the nuclei themselves interact with each other with the Coulomb interaction. And so the force is simply the electrostatic, the force on a given atom is nothing but the charge of the atom, the nuclear charge of the atom, Zi, times times the electric field generated by all the charges in the system, which are the density of the electrons and the density of the other ions. So basically, the formula that we would write in classical mechanics, let's say, calculating the force on a given atom as the local value of the electric field generated by all the charges around, and the times the value of the charge of the nucleus is the correct form. This is important results of the Hellman-Feynman theorem. And of course, the difficult thing is to get the density. But once we have the density, this is straightforward. And so the energy can be, the forces can be computed in a plane wave code. This is relatively easy. It's very easy to compute. Okay. Right. This is particular thing. This is true for plane waves because in other methods in electronic structure in which the basis set so the beauty of plane waves is that the basis set does not depend on the atomic position. The basis set is always the same. This is the good and the bad of plane waves. Plane waves are good for any configuration because they are always the same. This makes what we already saw yesterday, that sometimes the convergence may be slow because basically we are using the same basis set for all possible configurations. There are other methods based on atomic orbitals or on augmented plane wave or LMNPO basis function, in which the basis set itself depends on the parameters, on the positions of the atom, and this complicates the expression for the forces. For plane wave, in a plane wave formalism, the expression that we end up is the classical one. There is no extra term due to the fact that the basis function depends on the position of the atoms, because they don't. Okay. The only thing is when we perform, as Paolo Giannozzi was explaining yesterday, we are not really using the bare Coulomb potential because it would require a cutoff of very high value, and even for the simple atoms, and so we use pseudo potential. What one needs to calculate is not the derivative of the external of the Coulomb potential, but the derivative of the pseudo potential. But again, this is a kind of technical thing, and the expression is basically the sum of two contributions. The interaction of the density with the variation of the pseudopotential of a given atom and the direct ion-ion contribution to the forces. And so the evaluation of the forces is cheap, is a cheap byproduct of the electronic structure calculation. And once you have the forces, then you can use the forces to look for a good configuration. So if you started with some trial geometry, you can follow the force either by in a relaxation scheme, or you may want actually to study the evolution of the system at finite temperature, and then you want to really do molecular dynamics following Newton equation. Or if you're interested in higher order derivatives, then we need to, on top of the SCF calculation, perform additional calculation that calculate this variation of the wave function with respect to atomic position, but this will be dealt with tomorrow with when we discuss formats. And so basically, let's say that we have our system. We started with some atomic positions that are not optimal, maybe a good guess, but not optimal. And we want to find the best. The simplest method is steepest descent, which is guaranteed to converge to a local minimum if the step is small enough. I mean, simply what you do, you move the position of the old atom in the cell by a step size, which you can keep fixed. And if this step size is too big, you jump across, let's say, the valley, and so this may not be stable. But if you take the step small enough, you are guaranteed to go downhill. And if you repeat this sufficient number of times, you end up in the neighborhood of the local, of a minimum, which might not be the global minimum, but this is a big problem in general. When you have a multidimensional function like the total energy, what you can do is to search for the local minima, and maybe starting with different configuration, explore the landscape. But what the algorithm does typically is to go to the closest local minimum. There is, as I said, the forces can be used not only for minimization, but in general for dynamics. And one method that is very easy to implement is the Verlet algorithm, that if delta t, if the time step has the proper size, is integrate well the equation of motion, and therefore you can move around with in the so-called microcanonical ensemble. This means that you start for a system in a position where you have a certain potential energy, the value of the electronic energy of the system for that atomic position. And then as you evolve, and let's say you start with 0 velocity, as you evolve, you go downhill. Initially, you go in the direction of the force, but as you move, the system acquires some kinetic energy. And so if you apply the Verlet dynamics and delta t is chosen to be such that the integration is accurate, then you move in what is called the microcanonical ensemble, which is the system in which the total energy, sum of the potential and kinetic energy, is conserved. By doing that, you can basically move around and explore the landscape. One variant of the Verlet algorithm that is equivalent, numerically equivalent to the original Verlet algorithm is written in this velocity Verlet shape. I mean, the trajectory that the Verlet algorithm and the velocity Verlet algorithm produce are basically the same. But one nice thing of the Verlet algorithm is that the velocity of the particles, of the atoms, explicitly appear. Because instead, in the original Verlet dynamics, it's more efficient in terms of memory involved. You only need the position. In order to evolve the system, you only need the position, the current position, and the previous position. And then once you have the force, you can guess, you can evolve at the new position. So you don't need additional information. And the velocity can be estimated. The velocity at time t can be estimated for the at time t plus delta t and t minus delta t by this centered difference, which is okay, but it is advantageous in some cases, we will see, to have the calculation of the velocity at time t being performed together with the evolution of the system. So velocity Verlet is a reformulation which is algebraically equivalent to what we have in the first two lines in this slide, which, however, make appear the velocity of time t in the same step in the evolution as the position. And this is good because, for instance, this allows you to perform what is called damped dynamics. So the damped Verlet dynamics is a method that basically perform a dynamical evolution as for the with the Verlet algorithm. And if we don't implement this damping, it will produce the evolution in the microcanonical ensemble. But if you think, if you go back on this picture, you have the blue dot, which is the system in this idealized two-dimensional system, and has and suppose that instead of doing steepest descent, you are doing more like dynamics. You are doing Newtonian dynamics. What will happen is that as the ball roll down the hill, it acquires kinetic energy, and this kinetic energy will have a centrifugal component, will contribute a centrifugal acceleration. And so this is why the particle would not go to the minimum, but it will orbit around the minimum because it has the force that pull it toward the minimum, but the centrifugal acceleration that would keep it apart. So the damped dynamics try to put a break to this. And so basically what the damped dynamics does is to say, I want to perform molecular dynamics because when the velocity, but because this gives us some kind of inertia. This, if the velocity is different from zero, I can make longer step. But I want to do that only when these steps are in the right direction. I don't want to make longer steps that bring me away from the minimum. And so basically what damped dynamics does is that it projects the velocity in the direction of the force. So components that are orthogonal to the direction of the force that pull toward the minimum are basically killed. And so you are withdrawing kinetic energy from the system via this projection, but you are keeping the velocity if it is in the right direction. So to the extent the velocity is in the direction that local force suggests, then you keep and you actually accelerate in that direction. And instead, the component that would be orthogonal to the forces and that would give rise to this centrifugal effect, you don't want it. And so dynamics is a very simple method that basically exploit the fact that if you are force pulled toward the minimum and the velocity has a memory of the previous inertia. If the previous inertia is in the right direction, you keep it. If it would make you have a centrifugal effect, you remove it. And of course, when you overshoot, you go through in this way, you will go close to the minimum, and then you may overshoot. And so actually the projection of the velocity and forces may become negative. So because you have overshoot the minimum, at that point, you set to zero the velocity. That component of the forces is set to zero. So you basically project the velocity on the direction of the force, and you set to zero if this projection is negative, which means that you have overshoot the direction. Okay, this is basically what is implemented in Quantum Espresso when you specify that you want to use damped dynamics or quick min. And also there is, I think now in Quantum Espresso, another method which is called Fireball, which is, I think it's basically similar in spirit. I don't know exactly the details are maybe different, but this is the basic idea. You evolve the system toward the minimum and try to use the inertia of the system to get there more quickly. There are other methods instead that, given the position of the force, given the position of the atoms, make an estimate of the potential energy surface around the minimum and try to basically minimize this quadratic function. Assuming that the system is quadratic. Conjugate gradient is a method that is very good for strictly quadratic systems because at variance with the steepest descent method that is simpler to implement, so one thing that you can do is suppose that you are in x0, you have the force that point in some direction, and you choose not to do a simple time step, but you try to minimize in this direction. So along this linear, so you end up with a linear problem in which you want to find the minimum. Once you have done that, you are at the minimum. And if you calculate, now you have to find, this is the best you can do if you optimize along this direction. So when you are there, then in principle you can say, okay, I calculate the new gradient and I have a new search direction. And that would be the green curves. So the green broken straight line curve is what you would get if you choose the new direction, calculate it, and following up to the minimum in that direction. What you see is that even for this simple two-dimensional case, the steepest descent in which you minimize in the search direction is actually not optimal, because the new gradient, by definition, one can show that the gradient is orthogonal to the previous search direction, by definition of being at the minimum in the previous search direction, and imply that actually you are moving away from the right direction that would minimize the problem in 2 steps. So conjugate gradient is a method. Sorry, I went too far. Conjugate gradient is a method in which one finds out how to choose the next direction, the next search direction, so that what you gained in the previous step is not lost in a certain sense. So conjugate gradient is a very clever way to choose the search direction so as to not spoil the work that you have done during the previous steps. Problems of conjugate gradient is that well, it is guaranteed to convert. If you have a system with n degrees of freedom, it is guaranteed to converge at the minimum of this problem in n iteration step, in n search step But the problem is that this is guaranteed if the system is really quadratic. If you are not close enough in the quadratic to the minimum, the quadratic approximation may not be correct, and gradient may take longer. And if the number of atoms is big, even n, the number of iteration, which is the number of degrees of freedom. So for this reason, there is one other method which is very popular. It is quasi-Newton relaxation with this Broyden-Fletcher-Godfar-Shannon algorithm, which is the name of the 4 guys that propose it, in which basically it is similar to, I mean, it's always based on a Taylor expansion of the energy around a hopefully close point to the minimum, in which therefore you have, let's say, iteration, the last iteration xk, xk plus 1 is your new point that you hope to be a stationary point, and S is therefore the displacement. And if you expand the energy around your current position, xk, you can estimate, and you say we are close enough to the minimum, to the stationary point, then you can expand this and truncate at second order, and the things that enters in this expression are the displacement, the gradient of the energy with respect to this particular displacement, and this is something that you have access to by calculating forces or other first-order derivatives that you can calculate, and in principle to get to the minimum with respect to this displacement, you would need information about the matrix of the second derivatives, the so-called Hessian matrix. The Hessian matrix is something that you don't know during at the beginning, but you know relationship. When you move in one direction, when you make a step, and if you are in the quadratic regime, the variation of the gradient, so the difference between the gradient that you compute in your current position and the gradient that you would compute at the next position, are related to the Hessian matrix times the step size, if quadratic approximation is valid. And so the stationary condition is that the new gradient is 0, and then by solving this equation, you get that the step size in this Newton-Raphson formalism, if quadratic approximation is correct, is simply computed by the inverse of the Hessian matrix at the current point times the current gradient. If this is perfectly quadratic, this is fine, and this would give you the solution in one step. If it is quadratic and and you know the exact Hessians. Both of these two things are not correct, but you can have a method, and this is the BFGS method, that start with some approximation and improve on it. And the idea is that first, you cannot trust the quadratic behavior too much. I mean, it's probably correct if the step size is small, but it will not be correct in general. And so we can introduce a trust radius at largest step size, a safe value for the step size that should not be exceeded. And the Newton-Raphson step is estimated with the current estimate of the Hessian, of the inverse Hessian, times the current estimate of the gradient, but we don't go the full size of the step. We only limit our step to what we trust to be a reasonable value for the in which the quadratic behavior should be satisfied, first thing. And when you do this step, you have a new position, you have a new set of gradients. With this new gradients, with these new forces, you can calculate conditions that will allows you to update the inverse matrix, the inverse Hessian matrix. So, and you can, there are methods that update the Hessian matrix and then invert, or there are the FGS scheme that directly update the inverse matrix. And the inverse matrix is updated with basically the ingredient that you have been calculating. So the difference in the gradient, this gamma k is the difference in the gradients between the current point and the next point, and the current version of the Hessian and the step size and all this. This is formula that has been developed by the four guys, Broiden, Fletcher, Gottfried, and Chano, and this is what is implemented. So this is what is implemented with a safety device that is this trust radius that should not be taken too large, because otherwise it may become unstable, because this estimate may not be the right one if you are far from the quadratic region. With this, this is the method that is implemented in Quantum Espresso. And so basically when you say, I want to relax a structure, either you do by molecular dynamics with quick mean, or you do by this BFGS method. And the default is BFGS. And why it is the default? Well, it is a default because if you compare in a simple case, and this I think is, I don't remember, is a molecule, is a relaxation of a molecule, and you can have time dynamics, so this quick mean that I was mentioning, and if you calculate the energy as a function of iteration in the dynamics or in the relaxation step, you see that the blue curves become very flat very soon. BFGS, there are two variants because there are a couple of extra things that you can do, to reduce the memory use of the system, because in principle BFGS require that you store the inverse matrix, and so this inverse matrix may be larger. So there is a kind of limited memory version that store just the best previous iteration or just the three best and so on and so forth. So the more higher is the NDIM, the better is the approximation, but more memory demanding it is. So what you can see is in an expanded scale on the bottom line is that all the methods converge. The blue dots that is quick mean does converge, but let's say the more sophisticated BFGS that at the beginning of the iterations may have big jumps, actually, when you get close to the minimum, they do converge faster. So in principle, BFGS is due to the fact that it estimates the second order derivative. So the Hessian matrix has a better convergence dependence, so it converges faster when you get close enough to the minimum, but it may have it may be unstable if you are far. So if you start from far away, quick mean may be actually a good strategy to get close to the minimum, but then maybe one can switch to the BFGS minimization to get faster to the exact point. While instead, if you start very far from the minimum, the BFGS at the beginning may get in trouble. But okay, so the two methods are both valid in general, and some have advantages depending over the other, depending on what is your starting condition. If you start close to the minimum enough, BFGS is typically superior, and so this is why it is the default. So far, so good. We talked about forces. So this is to relax when we want to relax or make a dynamics in which the cell of the system is kept fixed. So if the cell of the system is kept fixed, we only deal with forces. We want to either minimize, get to the position of zero forces, or we want to make the dynamics. The problem, if you want to actually fully optimize your structure and you have a system solid, then you need also to choose the cell dimensions properly. And you saw yesterday how to do that in a simple case like diamond, in which there is basically, you know that the system is cubic and you want to minimize find the lattice parameter that has the minimum energy. This is simple. You can make a volume scan, a lattice parameter scan, and you get the minimum quickly. But you may have a more complex system with lower symmetry. The cell may have maybe non-cubic, may have up to 9 different, well, up to 6, sorry, different, a shape that is defined by up to 6 value, the size of the three three vector, the three fundamental vector, and the angles between each pairs of fundamental vectors. So there are six. The shape of a cell is defined up to these six parameters, and there is an overall rotation of the system that is always there, because the space is homogeneous with respect to rotation. But still, you have the shape of the cell to optimize. And this is a bit more tricky than you expect, because in principle, one could think that a solid is just a big molecule. So I have an infinite, we think of a chunk of matter as a finite set of atoms. And basically, if you think of it like that, there is no problem. We simply have to minimize the forces of all the overall atoms, and in principle, this is the same thing. The problem is that this picture is where you think of a finite chunk of matter requires a very big unit cell. It's typically aperiodic, because a finite chunk of matter does not extend to infinity. It has surfaces. So in principle, the relaxation just involving forces would require to be correct that we describe the piece of matter as a finite, big enough piece of matter in a big enough cell, etc. What we typically do instead is that we describe the system with in the periodic, infinite periodic approximation, in the infinite periodic paradigm, and because this is very advantageous. Bloch's theorem is based on the fact that we have this infinite periodicity, and we have therefore small unit cell, we have a point group symmetry that we can exploit. So this is all nice, but this makes the fact that the configuration of the cell of the system is not given only by the Cartesian coordinates of the atom in the unit cell, or of the atom, or the internal coordinates of the atom in the fundamental Bravais lattice, which is an alternative, equally good description, but they also contains the information about the Bravais lattice. So when we have to optimize the cell, the system, we need to optimize with respect or to X, which is equivalent, but then also optimize with respect to A, the component of the three Bravais lattice vectors, which define the cell shape. The static equilibrium, therefore, is obtained when the forces are vanishing. Okay, all atoms at equilibrium, but also the cell has vanishing forces, let's say extended forces. What are the forces associated to the cell? Are the stresses. So one can show that the stresses that we can compute are, which is a symmetric tensor, which has 6 components, are the forces associated to the fundamental Bravais lattice vectors. The fundamental lattice vectors are 9. I mean, the component of the fundamental lattice vectors are 9 because I mean, there are 3 vectors. The stress has 6 components. This is because rotations, stress are computed considering deformation that are without rotation. So removing the rotational contribution to the deformation. So this is why there are 6 rotation-free deformations, and this is what stress give us, because the 3 derivative, let's say, associated to the free rotation are zero by symmetry, by rotational symmetry of space. Okay, so in principle, therefore, what we need to do is to think of an homogeneous transformation, an homogeneous deformation in which all positions are deformed by a epsilon, by a deformation matrix epsilon, which is symmetric, so which doesn't have a rotational component, and the stress is the derivative of the energy with respect to this deformation scaled by the volume of the cell, and this is a first-order derivative, and so it is a situation in which the Hellman-Feynman theorem can be applied. And so there is no need to, in order to calculate the stress, there is no need to know how electrons vary when you deform the cell. There is no need to know how position, that are kind of additional variables in the problem, the position inside the cell vary. So if for a fixed, for a given ionic configuration at the minimum of the electronic problem, then these variations are not needed. And so we can calculate the first derivative of the energy with respect to the deformation in the spirit of Hellman-Feynman. The equation is a bit more complicated, and but let's say the concept that the ground state wave function is enough to compute this term is still true, and the theory was developed some years ago by Nielsen and Martin in Physical Review Letter, and in more detail in Physical Review B a couple of years later. Okay, and so if you compute, technically in the code, what you do is simply you have to specify. By default, it is not the default in Quantum Espresso is that you calculate the SCF. If you only do an SCF calculation, you don't calculate forces, you don't calculate the stress. If you do an SCF calculation and you set this stress variable true in the control name list, it will, at the end of the SCF, calculate the stress. And okay, this is something similar to things that you have seen yesterday. Nothing special, except there is this stress true. And at the end of the calculation, when you reach self-consistency, it will, at the end, enter a routine that computes the stress, and it will then write out the stress as a function of, the stress in atomic unit, so read by Bohr radii cube, or kilobar, converted to kilobar. Okay, and the pressure, which is also written here, is the average of the diagonal elements of the stress matrix, which in this case, they are all equal because the system is cubic, but in more in a lower symmetry case, they might be different. The pressure is defined as the average of the diagonal element. So far, so good. What happens if I do this for silicon and compare to what you have done yesterday with equation of state and extraction of the equilibrium geometry from the equation of state? What happens if you do the calculation with a not very high cutoff? Happens something a bit disappointing, which is the fact that you have a number of calculation that you have done with a script or with or repeating the calculation by manually vary the lattice parameter, and you can fit an equation of state like the Moore-Nagel equation of state, and you get therefore a numerical derivative, let's say, of the fitted curve, and you get one of this curve. And if you calculate the force, calculate the pressure with the formula that Nielsen and Martin provided, you get something which is slightly different. That has that cross the zero pressure, which is the condition of equilibrium, at a smaller lattice parameter, and it is not on top of the other. So is there some, what is wrong? I mean, this is, the stress should be the derivative of the energy. We calculate the energy, we calculate the derivative numerically. I mean, we fit with a function, and we calculate the derivative of the fitted function. So basically, we have calculated numerically the derivative, and we compare with the analytic derivative, and they are different. The problem is that if you think what you have done yesterday is that you have computed the energy as a function of the lattice parameter at a given cutoff. As you move around, the cutoff remains fixed. The number of plane wave that corresponds to that cutoff actually changes, and by Nielsen and Martin is accurate when the number of plane wave doesn't change. So if you focus, and so if you calculate, you make a much denser evaluation of the energy as a function of a lattice parameter, you see that the curve is kind of smooth, but every now and then has a jump. And this jump corresponds to the case in which, by making the cell a little bit bigger, new plane waves enters, and these new plane waves give additional variational freedom, and then you get additional variational freedom, the energy drop, because more variational freedom, the better minimum, and so you get a smaller value. And so the function that you are, the derivative that according to Nielsen and Martin is computed is, let's say, the derivative of the function where it is smoothly varying, does not take into account this drop. And this is a problem, and the problem is due to the fact, as I said already, that as you move the lattice parameter, some point is just inside the brilliant, the cutoff radius, or some point is just outside. When you change the lattice parameter and you make it bigger, the set of points that has to be inside this cutoff shrink, and some point that was just outside becomes just inside. If this plane wave that before was not present and now it's present is still relevant, then you may see a sudden jump in the total energy, and this is what spoil the nice the fact that the derivative calculated analytically should correspond to the derivative of the energy, numerical derivative of the energy, but it doesn't if we make the interpolation as we saw yesterday. So this is a problem. There are solutions. I don't want to I don't have time actually to enter in this. It's a nice thing, but it's not really used. But one thing that happens is that this is a defect that actually signals that the cutoff was not sufficient. because the fact that new plane waves enter is the origin of this jump, but the size of this jump depends on how well converged is the calculation. If the calculation is well converged, adding a few more plane waves doesn't change anything, and so these jumps are very small and do not contribute anything. And so basically this is what you see, the energy. So there are three curves here, three set of calculation with 16 Rydberg, 24 Rydberg, 32 Rydbergs, and all with the number of plane waves corresponding to one particular lattice parameter in the center, and keeping the same, changing the cutoff so that the number of plane waves doesn't change. And so you see that in one case, when the plane waves do not change, the curve is very smooth and the derivative is correct. But the problem is that the lattice parameter is computed, would have a minimum in a place which is not the real minimum of the more jagged energy that we show at cutoff, at a given cutoff. And by experience, doing calculation at fixed cutoff is better than doing calculation at a fixed number of plane waves. The solution to this is to make sure that you are converged with respect to the cutoff, because once the number of plane wave, the cutoff is high enough, doing it at fixed plane wave or fixed cutoff do actually have, they agree with each other, and so all the things are correct, and you can estimate the shape, in this case the lattice parameter, but in a more general case the shape of the unit cell starting from the stress. So okay, so let's forget this because I was I'm not I don't want to enter in these things because I'm kind of late, and we are not really using much that little trick. So the point is that one important message is that when you want to relax, use also the cell shape, you have to make sure that your conversion with respect to cutoff is reached, because otherwise you may have some problem. Minimizing, so optimizing the shape as a function of pressure, so finding the equilibrium for P equals 0 or at finite pressure is equivalent to minimize the enthalpy, and so this is what is done in variable cell shape relaxation, or if you want to do molecular dynamics, is what is done in variable cell shape molecular dynamics. For the variable cell shape relaxation, we have basically the same two options, either VFGS or molecular dynamics with frictions or quick mean. VFGS is simple in the end because basically you need simply to, internally the code pass all the variables that are relevant, the 3 NAT atomic position in crystal coordinate, and the 3 vectors that define the Bravais lattice vectors, and the forces that are passed through VFGS are just the projection of the derivative of the Hamiltonian of the energy of the enthalpy with respect to the internal coordinate, and this is just some projection of the forces times the Bravais lattice vector, and the derivative with respect to the lattice vector coordinates, which is something that can be computed from the stress, sigma beta alpha, the pressure that you want to impose, and again, things involve volume of the cell, the vector. And if you BFGS basically get this information and produce the same routine that works for the only thing is also working. If you want to do to do that, what you simply say that you want to, in the calculation, you choose VC relax. So you say VC relax, and by default, VC relax use VFGS. And by default, if you specify VC relax, it will switch on force calculation and stress calculation. And so the only thing that you need to make sure is that your cutoff and your K points, of course, are converge enough that the calculation of the stress is reliable. Okay, and if you do that in this simple system of arsenic, one system, one atom per cell system, so there is no force relevant, no relevant force, but the shape of the cell is important, and in a few iterations, in this case, in very simple case, in a few iterations, it converges down to a pressure which is within half a kilobar from zero, and this is the threshold, the normal threshold. If you don't ask, you can set the threshold to make it tighter, but it is okay. If you want to use quick mean, or if you want to do molecular dynamics, it's a bit more complicated because there is a problem of you need to assign a kinetic energy to the cell. And this is a kind of fictitious kinetic energy, and it's something that has been developed in the molecular dynamics community over the years. There are various methods. Anderson, how to say, pressure stat, I mean, Parinello-Raman method, Venskovic. So these things, Parinello-Raman and Venskovic are implemented in Quantum Espresso. And then if you want to do quick mean, you have to choose which. So they are, because in principle, the kinetic energy that you assign to the cell parameter are fictitious, are extra things that you want to use to sample the space around equilibrium. And so there is, I mean, one should read this paper to see. And there are reasons why Parinello-Raman proposed one, and there are different reasons why Venskovic proposed another one. So there are reasons behind that, and both are implemented in Quantum Espresso. And yeah, so one can basically, with quick mean, one can apply quick mean idea of killing the component of the velocity that are not in the right direction to get to the minimum. And it is easy to implement if you have knowledge of molecular dynamics. It's rather robust, as we saw, and does not assume to be close to the minimum. The con of this is that you need to specify a cell mass for the a fictitious mass for the cell, a fictitious time step, and so on and so forth. None of this is required for the BFGS. And so if you are experienced with molecular dynamics in variable cell, then maybe you can find natural to do that. If you are not experienced, you can just say, I stick with BFGS. Maybe it's not optimal if I start from far, but I don't have extra parameters to fix. And it works. it works. You specify VC relaxation, and in the cell name list, you have to specify that the cell dynamics is dump Venskovich, for instance, with this mass for the cell, and with delta T equal to 70. And if you do that, it converges quite fast. It converges quite fast to a different pressure, because in this case, I was requiring pressure equal to 400. Instead, in the previous case, I was using the default, which is PFGS, and imposing pressure equal to 0. Okay, so I think I stop here. I hope I didn't use too much time for Tone, and I'm open to questions. Or maybe Tone can, Anton, you can go on, and if there is any question later, I can answer. Thank you.
Okay, so let us proceed this way. And so I will start presenting the NAP method. So in a second or so, I will share the screen. Now, the first question. Can you hear me and can you see my slides?
Yes.
Yes. Yes. Okay. So good morning, everybody. My name is Anton Kokalj. I am known as Tone, and I come from the Jožef Stefan Institute. And in the next half an hour or so, I will explain the NAP method. Now, with the NAP method, we can model chemical reactions. And the characteristic of the chemical reaction is bond breaking and bond making. And this bond breaking and bond making is more often than not, well, almost always associated with the energy barrier. Now here you can see a very, very simple cartoon where we are breaking the bond between the blue and the red atom, and we are forming the bond between red and green atom. Now, if we picture chemical bonds as a mechanical springs, then we have kind of a parabolic potential energy surface, and this red curve here would be a projection of the potential energy surface along the reaction coordinate. And now I can define some interesting properties like reaction energy, delta E, which is the difference between the final state energy and that of the initial state energy, and the delta E will tell me something about thermodynamics of the reaction, whether the reaction is exothermic or whether it is endothermic. But then you see that as going from the initial state to the final state, I need to go over the energy barrier, and at the top of the energy barrier, I have the transition state, and then I can define the activation energy E star as the difference between the energy of the transition state minus the energy of the initial state. And this will tell me something about the kinetics. So why about the kinetics? Because we all know the Arrhenius equation, according to which the reaction rate constant is exponentially dependent on the activation energy. So basically here we have two terms. So this exponential term where we have the activation energy and this frequency prefactor, which according to the transition state theory is given by the vibrations of the initial states divided by the vibrations of the transition state, and the vibration along the reaction coordinate is discarded. But usually, if we would do a chemical reaction without a catalyst, the activation energy would be very high. And so the role of the catalyst is to lower this activation barrier and to make the reaction faster. And so if we are with the catalysis, if we use a catalyst, then one way is the heterogeneous catalysis. And we here have a snapshot of a typical let's say, heterogeneously catalyzed reactions. So we have some reactants, these blue and red balls. So they first need to adsorb, then they diffuse over the surface, and eventually they meet and they can react or not. And suppose that a product forms, then this product can diffuse over the surface and eventually can desorb. And then the projection of the potential energy surface along the reaction coordinate would look something like that. And we would realize that basically such an overall reaction consists of many elementary steps, where we can define the elementary step as a two, let's say, adjacent local minima that are connected by one activation barrier. Now, obviously, the potential energy surface is highly multidimensional, but the most I can do to plot the potential energy surface on a slide is to use a two-dimensional energy surface. And so here immediately we have some acronyms that will be important today. IS stands for the initial state. So this is, let's say, my reactant. FS stands for the final state. And so my elementary step would be going from an initial state to the final state. And of course, there are many paths how we can go from this state to that state. And there is a particular trajectory which will be of interest to us. And this trajectory is named as the minimum energy path. And as the name suggests, this is the path as going from an initial state to the final state that is characterized by the minimum potential energy. And then what we usually do is that we project this minimum energy path along the reaction coordinate, and this is how such a plot would look like. And here you see some definition of this activation energy and reaction energy. Now, when you do the NAP method, and when you see the result of the NAP method, usually you will have such a plot. So you will go from the initial state to the final state, and there will be several points. Now, what are these points? These points represent the whole structure. It represents a given snapshot of the structure. And then, of course, the energy of such a structure. So this would be the initial state, this would be the final state, and this is the transition state. And this particular reaction is, let's say, a transformation of a nitrogen molecule on the surface from a perpendicular to a horizontal structure, and something in between initial and final state, we will have the transition state. Okay, so why is this activation energy so important? Well, it is a good criterion to judge whether a given chemical reaction is kinetically feasible at a given temperature. And so again, here I am writing this Arrhenius equation for the reaction rate constant. And so you see it exponentially, so reaction rate constant exponentially depends on the activation energy. And so today hands-on will be how to calculate this activation energy, this E star. And here we have the frequency prefactor. And according to the transition state theory, it is the vibrational frequencies of the initial state and the transition state that enters this frequency prefactor. And you will learn tomorrow how to calculate the vibrational frequencies. But now, just if I want to estimate what would be the order of magnitude of this frequency prefactor, let me suppose that the vibrational frequencies of initial state and transition state are very similar. Now, for the initial state, I have 3n vibrational frequencies, and for the transition state, I discard the, let's say, the reaction coordinate. So is 1 less 3n minus 1. And typically, so if they would be very similar, they would cancel out, and I would be left out with one frequency of the initial state that points along the reaction coordinate. And let's say molecular frequencies are on the order of 10 to the 13, 10 to the 12 hertz. And this would be kind of an order of magnitude for the frequency prefactor. And of course, it can differ by several orders of magnitude. So if you would like just an estimate, you can look at this paper of Zdanov, where he tabulated the frequency prefactors for Bourion's reactions. Now here is just a simple example, so you can ask your question. So what would be a typical residence time of a molecule on the surface? Now, if we suppose that the desorption energy is 0.6 CV and we are at a temperature of 300 Kelvin, then the answer would be, if we plug in those numbers and take 10 to the 16 for the frequency prefactor, we would get that a typical residence time of a molecule on a surface with such a desorption energy would be 1 microsecond. In contrast, if the desorption energy would be 1 electron volt, then typical residence time would be 10 seconds. So you see that because this relation is exponential, so we can have a relatively small change in the activation energy, but concerning, let's say, the residence time or the reaction rate, if you're interested in the reaction rate, would change tremendously. Okay, now it's time that I introduce some jargon that is used in a NEP method, and this is image. So image stands for a given configuration, for a given snapshot of the whole system, and here is again the picture that I previously showed. So why the name image? Well, you can imagine that you would like to do kind of a movie of a chemical reaction, and this movie would be composed of several snapshots of several images, where each image is a given configuration. So from this point of view, I think that this name image is rather appropriate. Now, of course, the potential energy surface is, as I already said, highly multidimensional, and the most I can do on the slide is to use a two-dimensional potential energy surface, and basically this picture will be kind of a training potential energy surface for this presentation. And just pay attention that this R here, R is a 3n multidimensional vector, so, and it basically encapsulates all the coordinates of all the atoms. Now, do we know the potential energy surface? Well, we do not. We do not, and this is the problem. So what we know is, suppose that I have a given configuration, and the configuration would be now represented by a given point here. So I know the total energy of this configuration, and then in the preceding lecture of Stefano, you learn how to calculate forces. So basically, I know the total energy and the force, and then it is relatively easy to find local minima. Once I have the forces, I can use some simple method like steepest descent, or some more efficient method like BFGS. And then I would move toward the local minima. In contrast to finding the local minima, finding a saddle point is much more difficult. Now, an old and easy to realize method would be slowest ascent. Now, what is this slowest ascent? So suppose that I have a reaction coordinate along some bond length, then what I can do is I stretch the bond length and then do a constraint optimization. This may work well for dissociations, but it may also fail badly. And here is the example where it will fail badly. Suppose that I want to come from first local minima to the second local minima. And suppose that this reaction coordinate is the bond length. So I stretch the bond and then I do a constraint minimization. And so what I would, how I would proceed with such a procedure is that I would go here from one point to the next point and so on. And so you see, I would not really reach this local minima here. So this is example where this kind of all the slowest ascent method would badly fail. So we need some other idea how to locate the saddle point. And it is here where the NEP method comes in. So in NEP method, so the basic, let's say, input for the NEP method is that I choose, let's say, initial state and the final state. And then what I do is that I connect these two local minima with the elastic band. And this elastic band here is represented by this black curve. And now what I do is that I relax this elastic band with forces that are orthogonal to let's say, a reaction path. And here is a numerical recipe how I can do this. So suppose that I'm here at one point on this elastic band. This would be a tangent vector on this point, and then I can decompose the force to the perpendicular and to the parallel component. And so this tau is a normalized tangent vector, and this would be the numerical recipe, how I can get these perpendicular force components. And then I'm just relaxing this elastic band with this F perpendicular. And so what happens is, if I do this, is that from step to step, I would go towards the minimum energy path. And of course, we are assuming that our elastic band is super stretchable. And eventually, I would locate the minimum energy path that is characterized by perpendicular forces that are zero. And then the point with the highest energy along this reaction band along this elastic band is the saddle point, is the transition state. Now, of course, this was only a thought experiment, because here I used a kind of a continuous elastic band. Now, obviously, in computer, we cannot use a continuous elastic band. So what we do is that we discretize this elastic band into several images, like shown here. So these are these blue points. These are these discretized images along the elastic band. And now there is immediately a problem with this path discretization. Now suppose that, here I am at a given iteration. This is my elastic band, and these are my images. And these are the force components, perpendicular force components along the elastic band. And then, so I would move my elastic band along these forces. And then in the next iteration, my elastic band would look something like that. And now you see that this L double prime is the distance between, let's say, in the next iteration, these two images is L double prime, which is larger than L prime, and L prime is larger than L. And so going from iteration to iteration, if you would use this recipe, you can see that now the interimage distance is not anymore equidistance. And in several iterations, this can cause a lot of problem, because some images would come very close together, and among some images, the distance would be very, very large. And now how we can deal with this problem is that we connect these images with springs. And here is a picture. And then what we are using is kind of a spring force along this elastic band. And so if the distance becomes too large, then there will be a spring force which will try to keep the distance between images equidistant. Okay, and now here is how that would work in NEP. So basically we have two local minima. I connect this with some guessed reaction path, and then I discretize this reaction path, and I connect images with spring. And then I basically am relaxing this reaction path, or this minimum energy path with the NEP recipe. And so how it goes is the same as I showed before. So the true forces, I'm using just the perpendicular component of the true force, and I am using spring force along the reaction, along the elastic band. And this is called nudging. Therefore, nudged elastic band. Okay, but then what is crucial in NEP method is how we choose, because now we have this discretization, right? How we choose this tangent. And there was some, let's say, empirical experiments. What is the best? And it turns out that the best is to take this local tangent with respect to the adjacent image, which has higher energy. And here is a numerical recipe. And if we have a given image that is either a minima or a local minima or a local maxima, which is shown here, then we do kind of a weighted sum of these two local tangents. Okay, this is one point, but there is more. When I have this kind of reaction path as going from reactant to a product, so of course these two local minima, these are very interesting points. But then the additional very interesting point is the transition state. And because this is a very interesting point on the potential energy surface, I would like to locate it very accurately, and it would be desirable to have a higher resolution of points around the transition state. And to this end, I can use variable spring constants, which are arranged, let's say, from some maximum to some minimum value. And then the higher the energy, the larger will be the spring constant, which means that the images around the transition state will be, let's say, more close than around initial and the final state. And this is just a numerical recipe, is kind of a weighting between the minimum and the maximum. Now, even if I do that, and even if I discretize the reaction path with many images, still the point that is the highest in energy may not lie very closely to the transition state. And so now what is the idea is that I pick the image which has the highest energy, and then I climb up the potential energy surface along the reaction path with this image. And so what this climbing up means is that basically we are inverting this force component that points along the reaction path. So this would be a total force. And if I would use this, I would go down to the local minima. But now, instead of using this plus parallel force, I'm inverting, I'm using minus parallel force. And with this, so I'm inverting the force. Now I will climb up the potential energy surface along the reaction path, and sooner or later I will reach the transition state. And so this is called climbing image nudged elastic band. Okay, and now some practical aspects about the NEP calculations, because NEP calculations are usually difficult to converge, and the default initial guess is very important. Now, if in a quantum espresso, we just specify the first image and the last image, and we specify how many images we would like to use to discretize the reaction path, then the quantum espresso would use a linear interpolation. Now, in this particular example, it happens that if I do linear interpolation, one point lies very close to the transition state, but in real examples, this is seldom the case. And it is here that chemical intuition comes into play. If I have some idea how the reaction should go, then I can use intermediate images. And now in this plot, the intermediate images are shown by red points. So I can specify in the input the first image, and now here I would specify two intermediate images and then the last image. And so these intermediate images, they are used for steering. Basically, then what the code does is it makes kind of a piecewise linear interpolation, and then it suppose that I specify 10 images, it would put these 10 images equispaced along this piecewise linear interpolated path. So this means that basically these red points are not even used in the calculation, but they are used to make a better guess. Then only these blue points would be used in the calculation. And then the image with the highest energy would be used as a climbing image if we would specify, if we would request the climbing image NAP calculation. Now let me go to technical details, how the NAP input file looks like. So this is kind of a bare-bones structure. So it starts with the begin and the end keyword, and then it consists of two super blocks. The first super block is NAP specification, which is begin path input and end path input. And then is a kind of engine specification. This basically would be the pw.x specification, and this would be the starting and the ending keyword. And now let us focus on this NAP specification. This NAP specification consists of two, let me say, blocks. One is the path name list, which is mandatory, and the other is the climbing image card, which is required only when the climbing image scheme is manual. Now let us look a bit closer to this path name list. So this here we have several variables like string method. There are two, SMD and NAP. And this is the number of images. So how many images we want for the discretization. What is the climbing image scheme, the threshold, and the maximum number of optimization steps, and so on and so forth. And suppose that you do not know what these variables are. So how you do? You go to this input NAP description. In your virtual machine, you have this QUANTUM ESPRESSO input description button, and in Firefox, and there you can find the NAPX description of the input. And now we go to this engine super block, and basically this engine super block consists of the pw.x specification. So you saw yesterday this control system, electrons, name list, the atomic species card, the K points card. But then there is some speciality, because if we do a normal pw.x calculation, we just need configuration of one structure. But now in NAP, we need to specify at least first image and the last image. That is the initial state and the final state. And in addition to that, we can also specify intermediate images. And for this reason, because it's different than from pw.x, this specification of positions starts with begin positions and end positions keywords. Now here you have some explanation of these variables. So I will skip this because we are running late, and I will go to another kind of feature of NAP, and that is freezing. So what is this freezing? If we set use freezing to true, so what is it? Now, when we do NAP calculation, basically in each iteration, we are calculating all the images. And here I have the iteration 10. And so I can see the energy for all the images. And then I see the error. And here I can recognize that the error the error means how far away from, let's say, minimum energy path I am. So what are these, how large are these perpendicular force components? So you can see that here for 3 images that are highlighted by red, the forces are much larger than for the rest. And if I am using freezing, then in the next iteration, the code will just calculate these 3 images. Like you see here, image 2, this one, image 3, this one, and image 7, this one. And then you see in the next iteration, the forces are lower, and it is just the second image which still has large force, and then in the next iteration, only the second image will be calculated. And so with this use freezing equal true, we can have a smaller number of calculations, and we can speed up the NEP calculation. Now, some practical aspects, because NEP calculations are relatively difficult to converge, and it is here that experience is really important. And so to start with, it is very, let's say, helpful to start with a reasonable initial reaction path. And here the chemical intuition comes into play. And then one can use intermediate images to have kind of a more reasonable initial reaction path. And then it is a very good advice to start from relaxed initial and relaxed final states. So that means first pre-optimize initial state, final state, and then do the NEP calculation. There is the option in NEP, first last optimization true, but this is discouraged, because if you plug that in and you do not have the relaxed initial and final states, then the NEP will optimize also the relaxed and the initial states. And now let me just do a kind of simple demonstration of why these intermediate images can be very helpful. Now suppose that I want to dissociate a molecule on the surface. And in the initial state, I have a molecule high above the surface, and then in the final state, I have the molecule dissociated. Now, if I use a linear interpolation, this is what I would get. But this is not really very reasonable, because in reality, the reaction will be such that first the molecule will approach the surface, and when the molecule will be close enough to the surface, then it will start dissociating. And if I would use for the intermediate image, this orange snapshot, then my initial guess would be much more reasonable, and the NEP would converge much faster. Now, sometimes there are some questions that pop up, and one of the questions is how many images should I use? And this is kind of a tricky question, because it really depends on the case. But just to start with, typical inter-image distance should be in range between 1 to 2 more. Now, what is this inter-image distance, and where I can find this inter-image distance? Well, you can do a kind of a NEP dry run by setting n-step path equal to true. And then the NEP will just do a dry run, and it will report the path length and the inter-image distance. Now, of course, this is really a very rough suggestion, because this inter-image distance basically is a distance in 3n dimensional space. So in principle, it depends on the number of atoms in my system. But usually it happens that when I do a reaction, not all atoms move. There are just several atoms that move. And for this reason, it is this advice that is usually helpful. And it is very good to, when you construct the NEP input, that you first visualize how the reaction goes. And you can visualize it with XCRISP. And from this, you can see, okay, this is reasonable, this is not reasonable. So this is a good advice. And then the next advice is that we should just calculate, let's say, one elementary step. That is, we should just try to locate one transition state. Because with a CI scheme manual, in principle, we could do several in one calculation, but usually this is then quite messy and difficult to understand. Now, next question is about this variable spring constants. And it turns out, according to my experience, that this is not really crucial, and we can rely on defaults. It's okay. But the next, and this is the next advice is super important. And this is, do not activate climbing image from the beginning. because it is very good that we first relax reaction path to some extent in order to stabilize it. Because if we do not do that, what can happen is that in one iteration, it is one image that has the highest energy. But then in the next iteration, the reaction path moves, and it is the second image, the other image that becomes with the highest energy, and then this would be climbing image, and so on and so forth. And if we have this climbing image swapping, then the convergence will be awful. And so for this reason, it is a good advice to split NAP calculation in two parts. First, we do no CI calculations, NAP calculation. So no CI means that we do not request climbing image, and we relax reaction path to some, let's say, loose threshold. Here it is 0.8. And then in the next calculation, we plug in the CI scheme. This is the CI scheme auto, and we tighten the threshold, the convergence threshold. And this 0.05 EV per angstrom is the default in the quantum espresso. And here you see how in PWTK this can be very elegantly done. So we load the input from with this command, load from map input, and then we specify no CI calculation. We run the no CI calculation, and then we say restart mode equal restart, because we will restart from a previous run. We plug in the climbing image, and then we run the climbing image map calculation. Okay, and the next important thing is that when we specify first and the last image, and possibly the intermediate images, that you should use the same atom ordering. So you should not swap the atoms, because otherwise funny things can happen, and you will not model the reaction that you would like. And with this, I'm finished, and I think it is time to try some net calculations during the hands-on. So with this, I would like to thank you for your attention, and I will stop sharing.
Okay, if there are no questions, I suggest we can take 15-minute break, and we'll continue at 11:10. Okay?
Okay.
So thank you very much for your presentation.
Thank you.
So, yeah, it's 11:10, so Matic,
Okay,
floor is yours.
Thank you very much. So hello, everybody. Today I'll be guiding you through the hands-on session for the structural relaxations, nudged elastic band calculations, and we'll also cover some automatization with the PWTK scripting environment. So just to summarize the topics, let's say, the topics of today's two hands-on session will be the relaxation, the variable cell relaxation, the NEB method, and you have 4 examples that we'll be doing today. So the first thing to do is basically to open your virtual machine. I hope everybody has managed to do this, installed it by now. So you can go to day 2, open the folder in the terminal. So you should see something like this. So you should be in this directory, and the first thing I suggest you do is the daily update.sh, because we were updating some exercises. So I'll run this now. And as you can see, some things were updated. And one thing I would like to point out here is that we'll be using a couple of convenient functions that were prepared for you. Oh, sorry. I think I lost the presentation. So we prepared some functions for you for the HPC access. But to use these functions, you'll need to set up your HPC access in the right way. So you have here how to access Barbora, just brief instructions on how to make things easier. And I'll show you how to do this now briefly. So basically you can open another terminal. You change the directory to your home directory, and in this directory you have a folder .ssh. And in this folder, for example, you have this file that's called config, and you can open it with Emacs. So Emacs config, and you can enter here just these 3 lines. So the host is the host HPC. Host name is barbara.it4e.cz, and the user is your username that you're using to log into the HPC. And one additional thing that you need here is the public and private keys that you were using to log into the Barbora cluster. So I hope you have these in your virtual machine. If you don't, there are some instructions here on how to copy these keys. Essentially, you have to make sure that this private key has permissions, just read-write permissions. So you can do chmod 600 for this file. And this public key has to be, these 2 keys have to be the ones that you've been using to log into the clusters. So if you do everything correctly, if you follow these instructions, when you type HPC in the terminal of the virtual machine, it should take you directly to the Barbora node, to your home directory. So maybe let's wait a few minutes, and can you give me for you to set this up? And if somebody has any issues, please let me know. Or if for someone this doesn't work. You can use the reactions, and I'll see if. So maybe I'll go on since we're late on time. Just if somebody has any issues, let me know, and we'll try to solve them. The SSH should also work as SSH HPC if you're on your local machine, and you'll get into Barbora. So let's go directly to the exercises. And these are the aliases that we'll be using. So HPC is to connect you to Barbora, to your home, to the mirror directory of your system. rsync to HPC just makes a mirror directory on your HPC from the virtual machine. And rsync from HPC takes the folders from the system. So let's start with the example 1. I'll go here. So day 2, example 1, relax. And we'll open this in the terminal. And also it's useful to open the README. And we can see that basically what we'll be doing, we will be doing in this exercise is we'll be performing a structural relaxation, structural optimization of a graphene, which is basically a 2D carbon sheet with hydrogen atoms absorbed. We can check the structure with XCRISDEN. So if you're in this directory, you'll see 3 files. The first one we'll be using is this one, pw.graphene.relax.in. and you can open it with X-Grisden minus PW input and graphene relax.in. And since it's a two-dimensional system, we can reduce dimensionality here in 2D. And as you can see, this is our starting configuration. We can multiply it in a few directions to see a bigger sheet, but this is the structure that will be performing the relaxation of. So the structure seems okay, but let us still look at the input of this graphene relax.in so that you can see what you need to specify to perform a relax calculation with Quantum Espresso. So as you can see, the input is more or less the same. The important point here is that here in the control name list, you have the calculation type relax, while the default is SCF. And if you want to do relaxation, you have to specify this keyword. The system is defined here. So the provided index 4, and these are the cell parameters, number of atoms, number of atom types. And what's specific to the relaxation, let's say, method in Quantum Espresso is this name list ions. So yesterday there was a question about the electrons name list, which controls the, let's say, the electronic structure convergence. So the convergence of the SCF cycle, everything related to the SCF cycle is in this name list. And in a similar way, everything related to relaxations or moving the atomic positions is typically placed into the ions name list. And here we see the keyword upscale 100. And this basically just means this is a kind of a trick to increase the convergence threshold of the SCF when the convergence comes close to the minimum. And then we have the atomic species defined, the atomic positions, and the K points, as you saw in yesterday's exercises. So this is just the input briefly, and we can run this calculation simply in the virtual machine because this is a very fast calculation. You can copy this line from the README and run it. And what you will see is that this output file is being produced. So we can open this output file. And you can see that it looks much the same as the previous. First, it performs an SCF calculation with a given threshold. This was 10 to the minus 8, if you remember from the input. And then it calculates the forces in this case. And you see that the forces are 0 in the XY direction, and there are some forces in the Z direction. So the total force is still quite large. And you can see that we entered the BFGS geometry optimization, which is the default for Quantum Espresso. If you want to see which options you have for the relaxation, you can see, you can go to the PWX input description. And here you will find ion dynamics keyword. And the algorithms that Stefan was explaining today, you can set here. So you have to remember to set the case calculation relax in the control name list. And then you can specify iodynamics, either BFGS, damp for damp molecular dynamics, fire for a similar, an alternative to the damp dynamics, which is similar. And also for the VC relax, you have the BFGS or the damped options. And okay, so you can see that the calculation proceeds in steps. So after each step, the code displaces the atoms so that it minimizes the forces. So if we grab the total force, you can see that in each step, the force is becoming lower and lower. And in principle, once the force is lower than a threshold, we will assume that we achieved a minimum. So this force threshold is also here. You can specify it. This is the force convergence threshold, and the default is 10 to the minus third of a Rydberg. This, depending on the system, you can change as needed, but usually for a start, the default values are okay. So we have the total energy has to be lower. The change in the total energy has to be lower than the 10 to the minus 4 Rydberg, and the force convergence is lower than 10 to the minus 3. So once we can check the output again, and you can see that the job was done. And if the let's say the convergence was successful, you should see some kind of a line like this. In the output, BFGS converged in 6 SCF cycles and 5 BFGS steps, and it's the end of the geometry optimization, and you get the final energy. So let's look at what happened with our structure. So to open the PW out, you put PW out, PW graphene relax out. And we'll display all the coordinates as an animation so that you can see what happened. And maybe we can also display the forces. So you see that in the beginning, the forces are in the Z direction in this simple system. And as we go through the steps, the forces become smaller and smaller. And once they're close to zero, the system is in a minimum. And we see that basically we got one atom displaced out of the plane, which is expected for this kind of system. This is the minimum configuration for graphene. So this is let's say, a basic example of relaxation. Sorry. And so you can see that we already explained all this, the upscale 100, number of atoms in the cell. And we relaxed the calculation and we obtained this structure, which, as I said, this is expected, and it's called buckling in a sense. The next relaxation we will perform is of a graphene supercell, which is graphene supercell with an oxygen add atom. The point here being that you can also create supercells and study, let's say, systems but there are some tricks that you have to pay attention to so that your let's say, calculations are in line with what you did in the unit cell. So in this case, we have a 3x3 graphene supercell. And what you'll notice is, okay, we have graphene is not an insulator, so we have to use the occupation smearing. We have this ions nameless, which also has always has to be present in the relaxed calculation. And what we'll be using is that we reduce the number of K points. So in this case, we'll only be using the gamma K point. And the reason of this for this, I think you already know from yesterday, but let's just check the input. So we reduce the dimensionality to 2D, and you can see that basically now we have a much larger cell, which in reciprocal space means that the Brillouin zone is smaller. So we need less K-point sampling for these kind of systems. And it's typically good that if you start with a smaller cell, that you keep the density of K points consistent within your calculation. So for, let's say, if you started with 9 by 9 K points and you do a 3 by 3 supercell, the ideal, let's say, commensurate lattice of K points would be 3 by 3 in this 2D system. Because this is a 3 by 3 supercell. And we run this calculation the same as before, so just PWX. That's in. I wrote it out, but so it takes a bit longer, but you have the instructions in the README as well, which is, where is it? So this is the command that we ran, and we can visualize how the structure is evolving simply by looking at the output file. So I will not reduce the dimensionality in this case, just so that you see that this is basically, it's still an infinitely repeating slab. We just have it's separated by a vacuum in one direction. And in this direction, we only have the gamma point. And if we visualize the forces, now they're all over the place. But if in each step, the atoms move a little bit, get displaced, and you can see that the forces should be approaching zero as the calculation. You can try to reload this structure and you can see that it does it step by step. And you can also grab the force, for example. So you see that the forces are becoming progressively smaller, but you can also see that now that we have more atoms, the calculation takes a bit longer to converge and it's a bit slower. Also, it takes more computational time. So typically for larger runs, you should run them on HPC centers and on more realistic systems. So now we see that the forces are almost zero. And we can see that we got a bit of a displacement of the carbon atoms where the oxygen atom is on the surface of the. So this is the basics of, let's say, just relaxation. Let me close a couple of windows. And the next step that we'll be performing is the variable cell relaxation. And in this case, we'll be relaxing the cell of zinc, which is an HCP metal, which means hexagonal close-packed crystal structure. You have the lattice is defined with these vectors, and in the input you have two parameters. So the A parameter of the, let's say, rectangular of the lateral axis, and the C parameter, which can also be given in ratio to the A lattice parameter, or ALAT as it's called in quantum espresso jargon. And in this case, we have to specify a calculation that equals VC relax. And additionally, in addition to the ions name list, we also have to specify the cell name list after the electrons name list. So let's move to the example 2. So CD example 2, VC relax. Here. So here you will find, let's say, two inputs for VC relax. First, let's look at just this one. So we can visualize the structure again. In this case, we don't reduce the dimensionality, and you can see this is the A parameter, and this is the C parameter that will be changing in the construction. Also notice you only have two atoms in the cell. So if we run the calculation, you can just keep closing the window. So, yeah. So day 2, example 2. So we can run the calculation much the same as we did for the relaxation. But let's look at the input file with the Emacs mode, so you can see the differences with respect to the relaxation. So you have calculation equal to VC relax now in the control name list. Again, we have a metal, so you need to smear the occupations. And you have to specify these name lists. The name lists have to be here, but since we're using the default values, they are empty in this case. If you want to see which values you can specify, you can go to the documentation, and you can see that you have the cell name list for the cell and the ions name list for the ions. And you can see that we can look at the output in this case. Okay, it seems to finish. And as Stefan was showing today, once you compute the stress, so here, because we have a symmetric system, the force is 0 by default. So if we're just doing a relax, the system would think it's already in the minimum. But since we're doing a VC relax, you also get the total stress or the stress calculated on the cell, the pressure that's applied. And this is what's basically being minimized in the case of this example. So the forces on the atoms are 0, but the stress is the pressure is becoming lower and lower as we converge to the calculation. And in the end, you'll see that the, let's say, total pressure should be low. And finally, you should get an output of the final cell, which I think is... So, and you will get an output of the cell parameters for the final structure. So you see that our cell parameters changed a bit. So we started with so you see that the calculation converged in 18 steps, and that the cell changed slightly. We can check this with X-Freeze then. And what you should see is here is that the cell changes, but the atomic positions remain basically the same, because there are no forces in this due to the construction of the cell. So for the next, a bit more complicated example, we'll be running it on the HPC. So I hope by now you managed to set up the HPC access. So I suggest you write rsync to HPC, this directory, which will basically make a mirror directory on Barbora for you. Should see something like this. And if you type HPC, now you should be in the example 2 VC Relax. And here we prepared, let's say, a basic submission script for you, run Urea with 8 CPUs. And here we'll just be using the Quantum Espresso that was that's already installed on Barbora. So you can submit this calculation with sbatch, run Urea VC Relax, and you can check if it's running. So what is this example? So in this case, we have a molecular crystal, and you can see that this structure is a bit more complicated. So what we expect is that there will be some forces between the atoms, and the shape will change as well. So this calculation is more heavy simply because of the just the complexity of the system increases. But the point is, you can, in principle, relax both the atomic positions and the cell at the same time. And this calculation takes a bit longer, but you can retrieve the files with rsync from HPC, and you can write star out just to get the output file so that you don't copy everything at the same time. So let's open this with Experiment to see what's going on. So this is our molecular crystal. You can see that now we have forces. Okay, I'm using a shortcut here, but you can display the forces as display and forces, or click F on your keyboard so you'll see them. And so now you can see that it performed 12 steps. And you can see that both the cell and the atomic positions are changing very slightly, but they are changing. And we can update the file. And we can also maybe look at if it's finished or not. So you also have the command HPC SQ, which should tell you if the calculation finished or not. So for me, it took 1 minute something on the HPC, whereas on the virtual machine, it would take a lot longer. So do you have any questions up to now about the VC relax examples? Did you manage to run them? Or am I too fast? Okay, since there are no comments, I assume everything is working. And we can go on to the NEB example. Here I just briefly summarize what Tone was saying before in his lectures. So NEB is the method to identify subtle points on potential energy surfaces, which typically correspond to the transition states of chemical reactions. This is according to transition states theory. And in this example, we'll be looking at a very simple hydrogen molecule dissociation on an aluminum 100 surface. And we'll be using this intermediate image trick that Tone described very well. So instead of just providing the first and last image for the NEB calculation, we will also provide a guess for, let's say, a structure close to the saddle point. And this is needed because, okay, we can visualize the input. So first CD to the example 3 NEB directory. Here it is. Let's close the completeness. So day 2, example 3, and you basically, the whole exercise is described here, but first let's just look at how the images are constructed, so you get an idea. No? Okay, we will not reduce the dimensionality. So in this case, the NEB generated 8 images. We can multiply this a little bit so that you can see that it is a surface. And we have a hydrogen molecule that's basically, and this is a very, the example is meant to be run quite fast. So this is not a realistic system, but let's say we start with the hydrogen molecule on the in the vacuum, and then the final image or the final state is the hydrogen molecule dissociated on the surface. Now, if we didn't use intermediate image, we can imagine that going from this point to this point, the molecule would start, the atoms would start moving farther and farther apart, but already far above the surface. But if we use intermediate image, you see that the first image is basically just the molecule moving closer to the surface, which is what we would expect according to chemical intuition. So the first 2 images, and then when it comes close enough to the surface, that it starts to dissociate. And the idea behind the intermediate image is this, that you can sometimes provide a better guess than that just a simple linear interpolation, because if you did just the linear interpolation here, you would have a bit of an unphysical system where the molecule starts dissociating even in vacuum. So let us look at the input now. So you have this NEB H2 dissociation in. And here everything, we have everything defined. So we have the begin keyword. As Tone said, we have a begin, sorry. And you start with the path name list, which basically specifies the parameters for the string that's connecting the two, the initial and final images. So we use the string method neb. We determine the number of steps in the path. You can use the optimization scheme, number of images, and these coefficients are connected to the springs that keep the images at approximately the same distance. we also have the climbing image scheme auto, which means that to use the climbing image, but we will change that in the PWTK script, and a path threshold, which determines how well converged the force criteria for the convergence of the perpendicular forces of the images. And we'll be using the freezing coordinates that Stone already explained in the lecture. So below this, this is the end of the path input. We have the engine input, which is simply quantum espresso input with the control system electrons name list. And this defines the STF and the typical as you've seen. And finally, for the position, there's a bit of a difference. So we have the begin positions keyword. And here we define, it's necessary to define the first image and the last image. And as you can see, we'll be fixing two coordinates. These are typically fixed in the first image. And here we also specified, let's say, an intermediate image, which guides our calculation. And when it's finished, we end the end input and have the end keyword for the net input. Okay. And this is also, let's say, a bit of a heavy example, so maybe it's better to run it. And I forgot that we'll be running this with a PWTK scripting environment. So basically what we do here is that we load this input for the nudged elastic band, and we'll be performing two nudged elastic band calculations. As you can see, we'll first perform a calculation without the climbing image. So we set this value CI scheme, which was auto in the input, to no CI. And we use a very loose path threshold just to get, let's say, an initial idea of the path. So this is the first calculation that will be run. This is the input that will be generated by PWTK. And then once this is finished, we'll perform a better, more refined, let's say, NEP calculation, and we'll restart it from the previous run. We'll be using climbing image, and we'll be increasing, let's say, making the convergence criteria more strict. So to 0.2, I think this is electron volt per Angstrom. These are force thresholds. Thank you. So I suggest you copy these files to the HPC. So hit rsync_2_HPC dot. And if you type HPC, you should find yourself in this directory. So in your home, day 2, example 3, NEP. And we prepared a PWTK version for you in the, let's say, in our work directory. So if you don't remember, this is Mont Dodge 3 DT 23116. And here you'll find the PWK 3.1. And we're looking for this executive PWTK. So you should use this line and then add --/ slurm to tell PWTK that we'll be using the submission system. And it will generate the submission script for you automatically with the details that we configured beforehand. So just by running this, you'll get a summary of the, let's say, the parameters that were used in the submission script, which Quantum Espresso is loaded, and we'll be launching this command, so this PWTK script. So if all goes well, you see that we're getting a few files, and these are the images, the initial inputs. This is the, let's say, these are the files that NEP produces, and this is the NEP output. And we can look at this NEP no CI out. And you see that here is a summary of the path variables that you defined in the NIP input. It first performs as SCF for all the images on the path. It reports the forward and backward activation energy, and it says which images will relax first. So in this case, these 4 images are being relaxed, whereas the first 2 are below the threshold already. And it performs these iterations, and this, let's say, initial path already converged in the first iteration. And once it converged, it started the next one with the neb auto in. This is done through the PWTK script. So here we have a stricter convergence threshold, and we're also using the climbing image. So you see that if you're using climbing image, you get a report which one is the image that's climbing. And this, in our case, is the one with the highest energy, is image number 4. And because we did this, let's say, trick of pre-converging the path a little bit, the image that's climbing is always the image number 4, and we have no shifting between images, which one is the highest in energy and which one is not. So this calculation is still running. Okay, I think it's done. So you should see something like this, job done, when everything is finished. So we can go back to the virtual machine. And we can retrieve the files from this directory. So we can use rsync from HPC and just write dot here to get all the files. Or if you want specific files, you can specify a regular expression. Just to get the output, you can do it like this. But now I'll download all of them just to be safe. So we performed the nudged elastic band, but what did we get? So for this purpose, we prepared a new plot script for you that plots the results. And you can see that it uses these 2 files, the interpolation file and the data file. So Quantum Espresso generates these 2 files here. The data file basically just contains the energies of the particular images. So you should get 8 points because we were using 8 images. And here are the values of the energy barriers. So if we plot, and the interpolation file provides, let's say, a guess of the path between these images. So this is a continuous file. It's not separated into points. It performs a guess of the minimum energy path along the reaction coordinate. So we can plot the result. And you can see that we got a barrier of about 1.2 eV. The climbing image, the one closest to the transition state, was number 4. And you can see that the reaction energy is exothermic for this H2 dissociation. So if we go back to the slides, as you can see, we ran all these commands. We plotted, and we can also, if you want, we can check the geometry of the transition state. Let's say it's using so to remember, the transition state was the image number 4. So you can see that our starting guess when we said that the transitions, the dissociation should start closer to the surface was okay. And the transition state is characterized as something in between the two minima, and it's closer to the surface than to the vacuum. Because we started with relaxed configurations, the initial and final image should remain the same. Do you have any questions up to now? Did you manage to run the example? Yes. Okay, if there's, let's say, no questions, we'll do just a quick PWTK, let's say, demonstration of how you can automate.
But if there is a question in the chat.
I don't see the chat. Sorry?
The question on the chat is, how have you generated these intermediate images?
It's a good question. So in principle, it's basically, let's say you have to use a structure builder or something. It's not automatic, and it's more of your personal guess than something that can be done generally. So in principle, it's requires a bit of knowing the system that you're working with. So in this case, oh, sorry, I got completely lost. In this case, where we have, let's say, as I was saying, when we have this hydrogen molecule dissociation, this intermediate image should be, let's say, you kind of expect that the dissociation will take place closer to the surface. So you generate an image that's somewhere approximately here. So I can even show the structure if you want. So it's this thing. This is probably the number 2. Let's see, it's one of these probably. So this is the, I guess, the initial. And the one is this one. So you can see that this intermediate image that we generated is a bit closer to the surface. And the distance between the atoms should be a bit, well, we didn't change it, but in principle, you could also increase the distance between the atoms a little bit more. So in this case, we just generated an intermediate image of an intact molecule closer to the surface. Because if we, let's say, if, for example, I now delete, so let's do it like this. If I delete this intermediate image, you see that immediately in the first step, the two atoms go apart, and now they just go linearly towards the final image. And if you remember from, I have too many things open, sorry. So here we basically guided the system to remain intact, at least until it's close to the surface. And this depends heavily on the system you're using. I hope I answered the question. I don't know. Okay, so I don't see any more questions for now. So maybe we can move on to the final examples. And if you have any more questions, please let me know any issues. So, okay. So yes, for PWTK, you have some links provided here if you want to learn more. You have some links provided in this slides that are uploaded in the, on the GitLab. And in this case, we'll be using it to analyze the bonding of a carbon monoxide molecule on the rhodium-100 surface. And we'll be performing basically 4 tasks. So the first task is the relaxation of the absorbed carbon monoxide on a rhodium 2x2 supercell. We'll then be calculating a charge density difference, which in PWTK is named divden. This is something that you can also calculate with, is calculated with pp.x. And we'll be calculating the difference in density between the carbon monoxide and the rhodium 2x2 cell. We'll calculate the projected density of states, or PDOS for short, for this system by employing a denser K-mesh. And finally, we will do an integrated local density of states calculation of the system. And for the steps, I suggest that you go to the README file, for example. So I will move now to the example 4. So we are here, example 4 PWTK. So first, let us look at this PWTK script, which is, you can open it with editor. And so this is the script that defines the whole workflow that we'll be using. So the first thing is that we define some PWX input data that will be the same for the whole system. So we prepared this in a separate script. If you want to see it, it's just, it's basically very similar to the input structure of PWX. So you have the control system, electron, ions, nameless, the atomic species, and the K points. the only difference here is the curly braces instead of the Fortran / nameless. And this is important into the PWTK script in this command. And here we just define the name of the calculation, which is basically carbon monoxide on volume 100, 2x2, 2 layers. We specify the output directory, and we also set up a prefix with this same name. So this is TCL. I don't know how many of you are familiar with it, but it's a useful language. So what this script does, it will load the cell parameters and atomic positions from the XSF file. This is a PWTK, let's say, defined function, and we can check that we have this XSF file here. We can open it with Xgrisden. So CO login. Sorry, forgot the XSF. So we have a CO molecule, some vacuum in between on the rhodium 100 surface. Okay. And so here we're loading the let's say information about the atomic structure from this XSF file. And additionally, we are fixing the last 2 atoms of the system. So if we check this XSF file, the last 2 atoms are basically the bottom layer of the rhodium slab. And then this is the, let's say, the way to run the PW calculation with PWTK. So I think we use this already a bit during the exercises, sometimes a bit implicitly, but this means essentially just run the PWX calculation with this name of the input and produce an output with the same name and out. Once this calculation, so the script will run this calculation, and once it's finished, you have this utility atomic positions from PW out, which will take the positions, the final positions from the output file of the relaxed structure. So this part covers the, let's say, the part 1 of this exercise, the relaxation of carbon and rhodium. And we already load the coordinates of the final positions. The next step that we'll perform is the charge density difference. And for this, we need to perform an SCF calculation. So instead of calculation relax, we specify calculation SCF. We use input clear we clear the ions name list because for the STF calculation, it does not make sense. And additionally, we specify the parameters for the pp.x potential, which is plot number 0. If you want to check what this is, so we can go to QE into descriptions, pp.x, and plot number, and you can see that the 0 is the electron pseudo-charge density. So what we essentially define here is the input file for the pp.x and the plot command, which now we choose to write this into the XSF file. So if you want output format 5 means XSF. If you want to check these commands, you can check them here. So you have the output format 5 3D XSF, and you have a few different formats where you can write this data. Flag 3 essentially means that we'll be doing a 3D calculation. And then we have this kind of a div-den name list, and this is specific to PWTK, where we basically specify the segments of the calculation. So the idea of the charge density difference is to calculate how the charge density varies of the total system changes with respect to the two components, to two or more components, let's say. So the first component, this is the charge density of the whole system. Then we separate the system into segments, which is basically the molecule and the surface. And this means the segment 1 to 2, if we again look at this file, we just tell them, okay, this is our molecule, calculate this charge density separately. And this is our metal, which is from atom 3 to the end. Here we put the weights of the different files. So we have the charge density of the whole system minus the charge density of the two fragments. And what we'll be looking at is how this charge density rearranges once the molecule is on the if you take the system separately or the two are connected. So one additional specification is this keyword div-den segment specification for the segment number 2. So here you have to specify because the carbon monoxide is a molecule, the smearing does not make sense because it's not a metal, whereas for the whole system, you have smearing. And using K-points, gamma is more appropriate for molecules. So this utility allows you to specify, let's say, details for a particular fragment. Also, if, let's say, in the case of an oxygen molecule, it should be spin polarized, you can specify here and spin equals 2. And this part will be valid for the segment of this second segment defined here. So with this ID. When we run, then we run this calculation with the div-den run. And what basically will happen is that this is a predefined workflow. It will calculate an SCF for this first segment and the charge density for the first segment, an STF for the second segment and the charge density for the second segment, and also for the third segment. The same for the third, and then it will make one file which will subtract all of them. And this will be, let's say, the step 2 of the calculation. And next, it will be, we will have we'll calculate the projected density of states, which is basically calculated with this project wave function .x executable. And here it's the input we define. So this is just, let's say, Gaussian functions are put on the points of the density of states to make it smoother and the change in energy. And then we will run this PDOS by increasing the K-point sampling, which means that in addition to the SCF calculation, we'll also perform an NSCF calculation with the same parameters. So these are the calculations, let's say, that it will run. The rest is data management. So I suggest we try to run the calculation. You can run this also on the virtual machine. So you can just write PWDK, bonding analysis. Okay. You can check. So bonding analysis, we can make a log file. You can copy it from here. So if you check, it's the PWX is running. And we can follow this log file with less. to see which calculation is performing. So it started with a relaxation that will take, I think, the longest. And in the meantime, while it's running, we can also check what's still left in the script to check. Is it? Here. So finally, project wave function.x generates a lot of files with basically for each atom, the S or P or the valence states are plotted, project. So the total charge, let's say the quantum orbitals are projected to the atomic wave functions of the valence states. So for each of these, you get files corresponding to, let's say, to the S, P, D orbital, whichever are present. And in PWTK, we define this utility, which basically sums all the contributions for the atomic orbitals for a particular atom. And in this case, we'll be using, we will sum the local density of states of the oxygen atom for the carbon monoxide, the carbon atom of carbon monoxide, and the fourth rhodium atom, which is the one that the carbon monoxide bonds to from our file. So you can see that now it finished, and it's plotted to this file, non-shifted Aldous PNG. And we get something like this. So these are the oxygen states, carbon states, and let's say the fourth rhodium atom states. You can see that this is indeed a metal. It has a density near the third level. And you can also see that there's some overlap between the states. So these are likely the states that are responsible for the bonding and are interesting for the analysis. And this final analysis will be performed at the so-called integrated local density of states, where I lost. So we, maybe I should also show the charge density difference result. So so this file was created. Then you can visualize this with XPrism. And you can say tools, data grids. And you can see that here you have a grid ranging from -0.1, but let's say you can see that we have red here means an increase in charge density, whereas blue means a decrease. And you can see that we have increased charge density close to the bond, which indicates, let's say, a chemical bond between the surface and the carbon molecule. You can also plot, let's say, an isosurface. I took the wrong one. Let's say 10.2. And we can see that we have, let's say, the greatest charge density. In between this, the carbon and the rhodium. So, and sorry for skipping, but back to the, let's say, the next task that we'll do is the so-called integrated local density of states. And as you can see, this plot we already obtained, and we see that there's overlap between these atoms. So what we want to do is, let's say, visualize these states separately, and we'll be performing visualizing them in these ranges. So for this reason, you have this so you have this ildos seot rodion.pwdk. And here you can use the energy ranges that you feel that are appropriate. We have them predefined here, so I'll just I'll copy this. I'm not very used to MaX. So this script will not work if you do not define these energy ranges. And as you can see, we'll be going from -6 to -5.5. And if we look at the so we'll be integrating from here to about here. And then the next one is from here to here. And essentially we're integrating these peaks. So we can run this calculation, so save the file. And you can run this calculation here. So this integrated density of states is a function of the pp.x. Which you can find here. So this is the plot number 10, and you have to specify the min and max in EV. And if it's not specified, the Emax is the Fermi level in the system. So we obtained a few files called ildos.xsf. We can, let's say, visualize one of them. And you can see, let's say that this corresponds to a bonding state or one of the orbitals. Maybe this can be an exercise for you to try to figure out which of these states corresponds to which orbital of the carbon monoxide. So let's say as the final part of this exercise, we'll try to automatically plot all of them. So again, we should input the energy ranges here because I'm lazy. So this is the script: visualize ildos CO loading PWDK. So I'll just copy it here. Make sure to delete the hashtags if you're copying. And we launch it with PWDK. And now you see that in a similar way that we plotted the orbitals the first day for benzene, now we are plotting them here. But hopefully now you understand a little bit more what's happening. And in the end, you can see that some of the, let's say, non-bonding orbitals of carbon monoxide are filled, and there's some charge gravitination to this in the system. Okay, I think this is it for this exercise. If you have any problems or questions, please let me know. And I hope you managed to run the exercises.
Okay, I think
Okay.
that there are no questions for
No.
now.
Okay.
So thank
Okay.
you for your lecture. And now we should have a lunch break, and we should meet at 2 p.m., I think. So let's have a break and see you later.
Bye.
Okay, so this lecture is about different functionals. I mean, the basic has been presented by the first day, mainly the local density approximation and the gradient correct. I will briefly mention them as well, but then I will, there are many more functionals that people have invented, has formulated, and there are many labels like bit relief, exit exchange, PBE, V80, Perdizzung, all these things are labels that determine one particular functionals, and so they are too many to go in detail in each of them, but we can class them gather them in groups, let's say, in functionals, more and more complex functionals that go from the simple but not very accurate so-called Hartree word to the very accurate, in principle, very accurate functionals that can reach what is called chemical accuracy. Chemical accuracy is something that, say, a figure of merit proposed by chemists, which is about having energetics of systems accurate to the kilocalorie per mole level. Kilocalorie per mole is something like 43 millielectron volt per unit, or 3 millirydberg per unit. And so simple functionals like local density, local spin density, are simple, have been successful in a number of systems, but they are not very accurate. Gradient corrected functionals have improved on that, especially on the energetics, by including some measure of inhomogeneity through the value of the density and the gradient of the density in the local point. There are more refined functionals that include also estimate of the local kinetic energy. These are so-called meta-GGA. And then there are really more complex functionals that are mixing Hartree-Fock and DFT, let's say, formalism to get higher accuracy. And then there are really, really complicated functionals like RPA that we will not touch about, but let's say is a limit one can tend to. Yeah, so basically depending on what are the ingredients that are included in the functional, one can group these functionals in different families. And so, okay, this is the same Jacob ladder, let's say, picture that is dear to Perdue, that is one of the designer of many of these functionals. actually many of these functional has a P in their acronym, and this P most of the time is the name of Perdue. Okay. If you want to have a kind of historical view of what was the field up to, let's say, late 80s, there is this Review of Modern Physics paper, Review of Modern Physics in 89 by Johnson Gunnarsson, that basically discuss the good and the bad of LDA and the first gradient corrected function. So as we saw the first day, we have the Eulenberg-Kohn theorem that say that in principle, all the system, all the chemical problems that are related to ground state properties of our system could be studied if we have access to a functional of the density that incorporate the kinetic energy and the electron-electron interaction. And then if you have this functional and you couple it with the interaction between the density, the electron density, and the external potential, you get a variational principle that should give, in principle, the correct result. The problem is that this functional f of n is not known explicitly. You can only know the value of this functional if you solve the problem, but then this is exactly what we would like to avoid. This is why Kohn and Sham, 1 year after Eulenberg and Kohn, propose a trick, the Kohn-Sham formulation, in which they introduce a fictitious system of non-interacting electrons, so electrons for which the electron-electron repulsion is absent, and for which the Eulenberg-Kohn theorem is valid as well, but with the kinetic energy only. And in this way, there is, due to the Eulenberg-Kohn theorem, an analogous relationship that, given the density of the system, can there is a functional which is the kinetic energy of the non-interacting system with that density. And combining these two and the electrostatic energy, the classical electrostatic energy, the so-called Hartree energy, we can redefine we can split the functional f of n that we don't know in a sum of three terms. This kinetic energy of the Kohn-Sham, of the equivalent Kohn-Sham system that we can be introduced has been introduced by Kohn and Sham, the electrostatic energy, the Hartree energy, and a remainder. And this remainder that contains all the complexity that cannot be described by ES and EH is called exchange and correlation function. And then with this definition, the minimization problem for any system can be written as the minimization of a functional that contains the kinetic energy of the non-interacting system, the Hartree energy, the exchange and correlation energy, and the coupling with the external condition. And then if you perform the functional variation, you obtain that the equation that needs to be solved are the Kohn-Sham equations, in which the electrons are independent, because this is the Kohn-Sham system hypothesis. They move in a so-called Kohn-Sham potential, an effective potential that one can work out is actually the sum of three terms. The interaction with the external, the direct interaction with the external potential, so the interaction of the electrons with the nuclei, the Hartree potential, so that comes from the functional derivatives of the Hartree energy, and the exchange and correlation potential that comes from the derivative of the exchange and correlation function that is defined implicitly in the in this expression that I showed you before. And this is a major step because the problem, the non-interacting problem, we can solve. The ground state of the non-interacting problem, if we have the effective potential, can be solved very simply. You solve the one particle Schrödinger equation of these electrons, non-interacting electrons in an effective field. These orbitals are by nature of the equation that you solve orthonormal. The density associated to the ground state wave function of this non-interacting system is the Slater determinant that you can build from the lowest line eigenstates of this single particle orbital, single particle problem. With this single particle orbital, you can build the corresponding density, and with this density, you can feed back this density in the constant potential, in particular in the Hartree potential and in the exchange and correlation potential. So if someone gives you a functional form for the exchange and correlation potential, then this set of equations is a closed one, and you can basically look for the solution, the so-called self-consistent solution, in which these three equations are satisfied at the same time. And the advantage of this approach is that the solution that you need to look for is basically a self-consistent potential in which the electron move independently, and when you reach self-consistency, this is the final result is the correct density of the system, and if you feed these eigenvalues and the eigenvector in the expression for the energy, you get the exact energy. So in principle, this is as simple as solving a mean field equation, but it is exact. It is exact provided you have the exchange and correlation function. That, of course, we don't have. And so actually all the difficulty, let's say, has been swept under the carpet of this exchange and correlation functional, and now we need to basically make approximations for the exchange and correlation functional to and approximation for the change of correlation functional will determine approximation for the change of correlation potential, and then each different type of functionals that we will discuss will correspond to different approximations. The simplest approximation that, well, why this idea can be thought to be a good approximation. In the end, we haven't done anything. We haven't solved anything. We had an unknown functional, sorry, the f of n. We single out the constant kinetic energy. We single out the Hartree energy. We can calculate the interaction of the density with the external potentials. Why should be any better better than our starting point to try to address this problem? The reason is that the exchange and correlation functional, although very complicated, is a very small, a relatively small fraction of the total energy. The biggest contribution this is the total energy split up of a manganese atomic calculation, and the biggest contribution is the direct interaction of the electrons with the nuclei. Second is the kinetic energy of the electrons. Then comes the electron-electron repulsion in the R3 formulation, and the exchange energy. So this was I think an R3 calculation. So the exchange energy can be computed, and the exchange energy is a small fraction of the total, is small compared to the other contribution, and the correlation energy that is not included here is smaller than exchange energy. So exchange plus energy are a small fraction of the total. Approximations, simple approximation that you can make for this contribution to the total energy is not expected, but let's say one can hope, there is some hope that reasonable approximation for this small contribution to the total energy will end up to give a approximation, a useful scheme. And this is indeed what happened. And so the first, let's say, simple thing that you can do is the so-called local density approximation, which is similar to the Thomas Fermi approximation. The Thomas Fermi approximation is a simple approximation in which you try to model the kinetic energy of a system in terms of its density, and you say that the kinetic energy of the system, global kinetic energy of the system, is a sum of contribution, each coming from a small volume of the system, and this small volume of the system is treated as if it was a homogeneous electron gas. And this is not very successful. It has some qualitative feature that, let's say, maybe give some intuition, but definitely is not quantitatively accurate. But the Thomas Fermi approximation applied to the kinetic energy of the system, which is the second largest contribution in the total energy, while LDA, or local spin density, is the same type of approximation, but applied to a much smaller term of the energy. And so the hope is that in this much smaller, when applied to this much smaller contribution, the approximation is useful. And okay, so this is a cartoon saying that what I just said in words, that LDA was proposed already in the original Consham paper, and basically replace every, let's say, write the exchange correlation energy of every system as a sum of contribution of local terms, in which every single small volume is approximated by the contribution that that volume element would have in a homogeneous electron gas of identical density, and it's very simple to compute. Okay, and again, the advantage is that it is applied to the small contribution, a small term in the total energy. Local density, local spin density, which is the spin polarized extension of the same idea, were very successful and were applied to a variety of systems with relatively good results. And I don't know, one can calculate also first ionization energy and get trends that are in agreement with the experiment, especially if you include spin polarization. You can calculate energy associated to excitations that change the symmetry of the solution. So you excite from an S shell to a P shell or to a D shell, and with more or less reasonable success, you get numbers that have useful description of the system, and compare relatively well with experiments, much better than R3-Fock or the X-alpha functionals that were kind of historically their competitor, let's say. And then it has been used for many properties, studying the transition of system under pressure, binding energy of small molecules. And one thing that is evident is in these systems, that simple system that has been studied at the beginning and has been basically confirmed in the subsequent study, LDA give typically good geometries. Let's say bond lengths, bond angles are relatively good, within a few percent. Frequency of vibration are also reasonable, a bit stiff if you make an average about around different systems. One characteristics that tends to be systematically inaccurate is that the binding energies, so the binding energy of molecules or of crystals tends to be overestimated. So when you form a molecule, H2 or lithium or oxygen, the binding energy that you get, so the binding energy is the energy difference between the energy of the bound system and the energy of the isolated atom, is typically overestimated, and maybe also quite a bit overestimated. So as a summary, a quick summary of this experience, let's say, one gets that geometry are typically good, within a few percent. Cohesive energy are typically too large, and the elastic properties are typically a bit too stiff. So also the phonons are a bit stiff, but basically more or less it is reasonable. Larger certain materials like transition metals may have bigger errors, but overall the description is not too bad. So at the beginning, LDA was super successful. I mean, people were very happy with LDA. There were some discrepancy, systematic discrepancy with the experiment. Typical systematic discrepancy is that band gaps, calculated as differences between the last occupied orbitals and the first unoccupied orbitals in a calculation, are typically too small compared to experiment. But this has been then shown later that this is not actually a deficiency of the functionals chosen, so it's not a fault of LDA. Is the scheme, the DFT scheme, the consortium scheme that is not expected, is not expected to describe band gap. In order to describe excitation energies, electronic excitation energies, one needs to use other methodology like GW or time-dependent DFT or something more complicated. So these, let's say, failures on band gaps is something that happens, but one should not blame LDA for that. It's not it was not designed for that. It's not in its possibility to produce good band gaps. Okay. GGA, so people were very happy with LDA at the beginning, but as time went by, people were starting seeing that there is this overestimation of the binding energy, which was kind of not very nice. If you're interested in thermochemistry or basically reactions in general, then, or comparing different phases, having an error in the binding energy is not a good thing. And so one of the next step is to going beyond the local density, going beyond assume that the system is described as if it was an homogeneous electron gas locally. And actually, you can see that there are cases, there are many cases in which the density is not homogeneous at all, in the sense that even if you look at atomic densities for beryllium, basically, and you compare a plot of the density in black and a plot of the so-called scaled reduced gradient, which is an adimensional quantity, which is the gradient of the density divided by the density to the 4/3, so that this is a dimensional quantity. What you see is that this green curve is relatively small or not too large in a region where the density is large, but there where the density decays, and so this happens at the surface, and so this will happen at the surface. If you have a macroscopic system, this will happen where the density decay in vacuum or on the frontier of any molecules, this reduced density tends to diverge. So there are regions that are basically where when you try to create a bond or a new bond or break a bond, you are pulling apart atoms, the density develop, the density become exponentially decaying, and in that region, the gradient the reduced gradient become larger and larger. So definitely we are not in the local density place. Sto facendo lezione. And okay, so so the first attempt, the first attempt, as Paolo mentioned, were actually failing because when people were trying to do just a Taylor expansion of the function around the homogeneous system, but this was not successful. But let's say the first successful schemes were called generalized gradient approximations, and proposed by Perry and Wang in 91, and later, 96, there was a kind of proposing the same ideas, the same concept, but with a more user-friendly functional form, and this has become very popular, and is PBE, the PBE functional. So PBE and Perry 191 should be numerically very similar, and PBE has been preferred because of its more nicer functional form. Okay, and these generalized gradient corrected functionals basically have the typical form of a term that depends on the density, so it's LDA-like, multiplied by an enhancement factor that depends on RS, which is another way of specifying the density through the so-called Wigner-Seitz radius of the associated to a given density, the degree of magnetization, local degrees of magnetization zeta, which is the unbalance between spin up and spin down density divided by the total density, and this reducer gradient. So S is this reducer gradient, and different functionals differ basically by the shape that they guess they provide for this enhancement factor. And the point is, and this is successful, and has been successful in reducing the error. For instance, these are formation atomization energies, so binding energies of a number of small molecules. And in R3-FOC, unrestricted R3-FOC, the error in terms of kilocalorie per mole is terrible. Local density, local spin density, half more or less that error, but is still large. And this Purdue 191 or PBE give very similar results, because in a certain sense, numerically, they are trying to do the same job, and they reduce this atomization error to a much smaller, so a quarter of what LDA, local spin density, can give. Right. And so if you compare with the corresponding atomization energy, experimental corresponding atomization energy in experiment, you see that there is a gradual, let's say, movement toward being more accurate. PB or PW91 are not perfect, but are definitely an improvement. Similar things happen for formation energy of a few materials. The energy is become a bit no, these are energy, or I don't remember. Yes, I think these are energies. So there is some error, which is definitely improved. Okay. So overall, making the long story short, the GGA compared to LDA improve cohesive energies, and the effect on lattice parameters is a bit random, scattering around the LDA results. Both LDA and GGA gives okay geometries. The big improvement is in the cohesive energy. And also for magnetic systems, GGA has been shown to be better. For instance, iron in LDA is non-magnetic, while it is correctly described as a magnetic when you use GGA. Okay. Right. Okay. More or less, this is the situation. And for instance, one can look at in the periodic table and compare phases of different elements, and compare elements that may form in FCC and BCC. And the general results is that GGA typically give the correct preference for the correct for the correct structure. And this is for the difference between BCC and FCC. Similar things can be done with more subtle difference between materials that can crystallize in FCC or in HCP. Okay. So much for, let's say, just this was a quick let's say, summary of the two main approximations that are used nowadays. Let's say, when people talk about standard DFT, they typically have in mind GGA, not so much anymore LDA, but LDA is also a simpler, rather robust functional that could be used. Typically, when people say standard DFT means GGA, and typically they means PB or some variant of it. Still, there are cases in which this standard DFT is not accurate, and there are classes of materials for which these approximations are not good enough. So trends are typically good, but weak bonds or system in which the overlap between wave function localized in different around different atoms are small, are problematic. And so basically materials in which the atomic limit persists in the solid, like transition metal oxide, rare earths, and so on. So in which certain atoms in the solid have some atomic-like feature are problematic because one thing that LDA and GGA do not fit well is the self-interaction correction. The self-interaction, the fact that electrons in Hartree-Fock, for instance, when you formulate the Hartree-Fock equations, when you formulate the Hartree-Fock functionals, you start with the exact Hamiltonian, but you have an approximate wave function, the single letter determinant. But if you proceed, you end up seeing that when you write the total energy, the interaction energy describes the interaction of each electron with the other electrons, and you write it as the interaction of the electron with the Hartree potential that contains all the electrons, including itself, and then you subtract the Fock operator. And one basic properties that the Fock operator has is that it cancels the self-interaction that shouldn't be there. So Hartree-Fock is very often a terrible approximation in terms of energetics, but has these self-interaction properties enforced exactly in the theory. When you replace Hartree-Fock with an exchange relation functional obtained with LDA, GGA, or others, you are replacing a term that describes the exchange in Hartree-Fock that is correctly self-interaction free with an approximate description. And this approximate description may have may not cancel exactly the self-interaction. Where there are orbitals that are very localized, the self-interaction is bigger, and therefore this error in the self-interaction cancellation may be more severe. And so this is why transition metal oxide, rare earths, and other systems in which atomic orbitals, so strongly localized orbitals, are relevant, may be problematic. And so we will see what are the functionals that have been then introduced to deal with this. Another type of interaction that is important and is basically everywhere is the so-called van der Waals interaction, the dispersion interaction, which is a correlation effect. So van der Waals interaction, the elementary theory of van der Waals interaction is related to the fact that you have fragments, and these fragments may have density fluctuations, and this density fluctuation in different fragments may correlate and via dipole-dipole interaction, and this correlation end up giving a contribution to the energy which is attractive. This correlation is clearly a non-local interaction. So it's something that cannot be described via local density or gradient correction or anything that focuses on a single point in space, because it's actually an interaction between fluctuation, density fluctuation in different points in space. And so, but van der Waals is very important. All organic molecules, all organic molecules or crystals which do not have strong electrostatic or covalent. So the interaction between molecules that are neutral and do not form chemical covalent bonds, the van der Waals is basically the only interaction that remains, and so has to be described correctly if you want to describe properly their interaction. So it's a weak interaction, it's always there. Sometimes other interactions are stronger, like covalent bond or ionic bond, but when these other interactions are kind of out of the game, van der Waals becomes the only relevant or the most important interaction, and needs to be treated correctly and cannot be treated at the LDA and GTA level. So I will go through these two, let's say, kind of problems separately, and they have different functionals, let's say, that address these problems. There are self-interaction correction functionals. Well, the self-interaction corrected idea, let's say, and then there are hybrid functionals or the FP plus U that are being used in practice to deal with system in which the self-interaction error is important. So to say again, what is the problem? We may have a system, and let's say that we want to study the transition from, the formation of transformation of a system from a metallic phase to a oxidized phase, and this transformation involves transition metals. What happens is that when we are in the metallic phase, the wave functions of the metals, including the transition metals, are kind of delocalized on across the system, and therefore the wave functions or the Barnier functions or the, let's say, local orbitals that we can fluctuation of the density that we can identify in the system are typically spread out. And being spread out, they have a small self-interaction, because the self-interaction is basically inversely proportional to the typical distance within the orbitals, the relevant orbitals. And the self-interaction is small, and therefore also the self-interaction error is small. Instead, when you go to the transition metal oxide phase, the orbitals, there are orbitals that are strongly localized on the transition metal. They have very little overlap with orbitals in the neighboring atoms, and therefore this localized orbital has a very large self-interaction. And the fact that the DGA or LDA treat only approximately this self-interaction makes that there is a large self-interaction. So when you compare, let's say, you combine lithium with an oxide and you form a salt, so you have a lithium metallic object and an oxide, and then you combine them and you form a salt, what you get is that basically you are converting electrons that were delocalized on the lithium metal phase into orbitals that are localized in the compound on the salt, lithium iron phosphate or lithium manganese, lithium vanadite, etc. So you pass from state in the metal to localized state in the transition metal oxide or phosphate. And if you calculate the energy involved in this transformation, GGA may be have a big error. And this error is associated with the fact that the self-interaction error in one treatment on one side is very different from the self-interaction treatment on the other side, and so there is no basically cancellation of errors. When the nature of the two compounds are similar, you can hope on some cancellation of error, but in these cases, you go from a delocalized set for lithium metal to a localized state in the oxide. And so this is end up to produce a big error. What is the problem? The problem is the self-interaction. So if let's say the model system that describe that are in which the basic ingredient is this self-interaction are the MOT insulators, are the Hubbard-U models, in which you have a set of localized orbitals that are coupled by a hopping term, and somehow this hopping term is described by the overlap, the small overlap between the orbitals localized in on one side, on one atom, and the orbitals, atomic orbitals of the other atoms. And in some approximate way, this is taken care in LDA. I mean, the overlap, the wave functions of one atom, of the size of the wave function, the way the wave function decay in neighboring atoms is captured by LDA. And so this open term may not be super accurate, but it is qualitatively accurate. What is totally wrong is the fact that is very different for when you have on average one electron per atom, but occasionally these two electrons may be on different atoms, or they may be both on the same atom. And when they are both on the same atom, actually, there is an extra repulsion between them. And this is totally wrong in LDA. LDA is a mean field approximation, and therefore it kind of spread describe the interaction of one electron with the average of the other electrons, and is not able to describe the fact that at a given moment there might be two electrons on the same atom, and the energy of the negative ion in which two electrons are on the same atom is not, I mean, the combination of the energy, the comparison between the energy of the empty ion, the single occupied ion, and the W occupied ion in LDA are described as being in a linear relationship, and instead these three systems have a quadratic term that depends on that is strongly dependent on the self-interaction, and that is described by this U, and this is not described correctly by LDA. And this has consequences when, for instance, you want to study a system like iron oxide. Iron oxide, if you solve it by GGA, what you have is that it has, okay, iron contribute 8 electrons, but 2 of them are stripped and kind of attached to oxygen, and iron is left with 6 electrons. These 6 electrons are 5 of them occupy the one spin channel. The d orbitals of iron are completely filled on one channel, and then there is 1 electron left on the minority channel. And this 1 electron left in the minority channel in gradient corrected functionals tends to be spread over the 3 PV orbitals in the calculation. So basically, the result is that the system is metallic, appears to be metallic. There is a Fermi energy that there are 3 bands around the Fermi energy that corresponds to the orbitals, and these are all partially occupied. Okay. And the result is a metallic solution, while in experiment, iron oxide is a insulator, is a molten insulator. So to solve this problem, Perdue and Zunger propose the self-interaction corrections, or we can go in the direction of hybrid, so-called hybrid functionals, in which you say, okay, the self-interaction was correct in a trifoc, and so let's mix the 2 schemes, let's say GGA and a fraction of our trifoc. So we describe the exchange relation energy as a fraction of our trifoc plus the complementary fraction of a PB scheme or a B3 or D Young par functionals. And by choosing the parameters or by adopting parameters that are proposed in literature, we can try to get a better treatment of the self-interaction energy. Or one other scheme that is more originated originally from a model description of these Hubbard models is this DFT plus U, in which you take a gradient corrected functional and you add an extra term in the energy that should describe or should correct for this self-interaction error. Okay, self-interaction correction, which is not particularly used today because it's complicated, but the idea is that you should, in principle, write the functional as a sum of kinetic energy, R3, and the exchange correlation, and the exchange correlation should be such that when there is only one orbital involved, then one electron does not interact with itself. And so basically, if one modify the functional so that whenever the density or a part of the density can be written as a single, the density of a single orbital, then the exchange correlation energy should be 0 because one electron does not interact with itself. So if you use this scheme, you can formulate the problem in this self-interaction corrected formulation, which, however, is complicated because becomes orbital dependent, and each orbital needs to solve a different set of equations. And so in the end, this complexity makes that it is not used. For instance, quantum espresso is not implemented. But let's say historically, this is the paper in which Perdue-Zunger 81 they pinpoint that this is the problem, or this might be the problem in certain materials, that this self-interaction correction should be addressed somehow. The other way, let's say the next way people have addressed this problem is by trying to make better functionals in general. And the hybrid functionals can be, let's say, obtained by as a result of a theoretical scheme that try to derive at least a formal expression for the exchange correction function. And if you remember when I introduced the exchange correlation function, I said we have the you have the Holmberg interacting system, we have the Kohn-Sham non-interacting system, and these are kind of two extremes. We can think of a family of functionals in which, depending on a parameter lambda that goes from 0 to 1, transform the Kohn-Sham system in the correct many-body system. And we do this adiabatically. We do this continuously. And when lambda is equal to 0, we are in the Kohn-Sham case. When lambda is equal to 1, we have the exchange, so the correct many-body situation. And the prescription is that across this transformation, the density is kept equal to the density of the interacting system and of the Kohn-Sham interacting system that are assumed to be the same. If you do that, formally, one can write the exchange correlation energy as an integration over the coupling constant value of the expectation value of the interaction of the electron-electron interaction over wave functions that corresponds to the various strength of the interaction lambda. And so the density is always the same. So for each value of lambda, there is a direct contribution to the interaction energy, which is basically always the Hartree energy, and but there is a residual that will end up to be equal to the exchange operation function. And this is an integral. This integral, therefore, is one can work out, and as formally, this is therefore the integral of, so the exchange of correlation energy is can be extracted from the integration of this Coulomb interaction energy minus the common Hartree energy. And for lambda equal to 0, this actually is nothing but the Fock energy, the exchange energy calculated with the Kohn-Sham orbitals. And for lambda equal to 1, it is a correlated function. And so the idea proposed by Becke on the basis of this analysis is that what we need to do is to integrate something that for lambda equal to 0 is R3 Fock, and for lambda equal to 1 is something that could be LDA or maybe a GGA. And so it's a good idea to describe, could be a good idea to describe the integral of this quantity, making a trapezoidal rule approximation of the integral as an average of the value of lambda equal to 0 and the value of lambda equal to 1. And this is the first hybrid functional that was called half-half, but then it was further developed, and one very popular functional that follow these ideas is this B3LIP, which is a Becke 3-parameter functional combined with Lee, Yang, and Parr correlation. And the Becke 3-parameter object has a parameter that say what is the fraction of R3 Fock that you include, and then what is the fraction of gradient correction that you include, and what is the fraction of correlation that you include. And Becke figure out by testing a number of molecules what are the parameters that are good. And this very popular functionals has like 20% of R3 Fock, and the rest some combination of gradient corrected or LDA function. Perdue and co-worker then worked on this idea, and they figure out that they have some argument to say that actually the fraction of R3 Fock should be like 1/4, and then for the rest that they propose PBE and PBE exchange, 3/4 of PBE exchange, and 100% of PBE correlation, and PBE 0 is this combination. And then of course there have been others that have proposed different things, and when people do calculation with this hybrid function, sometimes they use this parameter of a fraction of R3 Fock as a tuning parameter that for different material may require some adjustment. So overall, it's a more complicated system, but there is some justification in these formal results that would give the exchange of correlation energy exactly as a coupling constant integration of interaction energies integrals. Okay. Technically, R3 Fock in plane wave is a very complicated object. It's not complicated, is expensive, becomes expensive, because basically the object that one needs to compute is the R3 Fock exchange energy. This is what you need to compute in Hartree-Fock. This is an ingredient of what you would compute in the so-called optimized effective potential. This is one ingredient of these hybrid functionals, either half-half, Philippe, or PB0, or a little bit different expression, but similar expression in HSC, which is another hybrid functional. This has this form, and it's very expensive to compute because it's a double sum over orbitals, and is basically the calculation of many Coulomb integrals, interaction energy of Coulomb auxiliary density that are obtained by making the product of a wave function at k and a wave function at k prime. And you need to do this over and over again for all k points, for all bands, for all pairs of bands and k points. And so when you want to calculate the Fock operator Vx apply to an orbital, what you need to do is to Fourier transform your wave function from reciprocal space to real space. For each occupied orbitals, multiply this wave function that you have transformed to one of the other orbitals, of the occupied orbitals, to get the density. Then you have to solve the Poisson equation, and so you have to Fourier transform back to reciprocal space. You get the Fourier transform of the density. Then you solve for the solution of the Poisson equation, which is trivial, but has to be done for each pairs of wave functions and each pairs of k points. Once you have this, you Fourier transform back in real space, because you have to multiply by the wave function itself and accumulate this on the term that in the end will be just the operator Vx apply over the wave function. So every time you want to apply the Hamiltonian, hybrid Hamiltonian on a set of orbitals, for each orbital you have to do all this machinery, which is very much expensive. And there is also a technical problem associated to the fact that this Poisson equation in the limit when k and k prime tends to each other, this q parameter is what go to 0, and in the limit for q going to 0, this integration is would have a divergence, which is a so-called integrable divergence. So in the end, the result is going to be finite, but has to be taken care properly. And so there are various methods that are implemented. One of them is the Gigi-Baldereschi scheme, in which one add or subtract a term that has the same divergence, and the term with the divergence can be integrated. The term that you add that has the same divergence can be integrated analytically, and we give a finite result. And the difference of the original function minus this term that has the same divergence does not diverge anymore, and so you can integrate it over a finite grid of k points, but it's all an extra complication of the system. And all this is implemented in Quantum Espresso, and this is one of the way to deal with the q plus g going to 0 limit. There are a couple of other ways in which one can try to solve this problem, and but the point that remain is that you need to perform a lot of calculation associated to this, making the product of two-way function, getting an auxiliary density, bringing the density to reciprocal space, solving the Poisson equation, bringing the Poisson, the contribution to the potential back to real space, multiplied by the wave function, and at the end of everything, finally transform back the result in reciprocal space. So this is why we do that, because this improve, at least for some molecule, it improves the result. And so if you calculate, let's say, PB0 with the plane wave, so with quantum espresso, has an energy which agree well with an independent calculation done by Kresse and co-worker, and agree well with calculation done with Gaussian, and agree well with experiment, and so which all these results are much better than the result that you would obtain with PBE, so without these hybrid functionals, and is anyway much better than pure R3-Fock. So combining a quarter of R3-Fock with PBE basically is an improvement. Okay, but it's much more time consuming because you have to do all this calculation, and it scales terribly with the number of plane waves, how many. So in order to calculate the kinetic energy and the local potential, typically in a normal calculation, you spend something that grows linearly with the number of plane waves, linearly with the cost of a single FFT, and linearly in the dimension of the grid, FFT grid. The non-local potential are more costly because it's the product of things that you can do on the plane waves, but you have to do for each band or for each projector that are more or less in the same order of the number of bands. The Fock operator is much more. So the coefficients in front of, so this is going to be, as in the non-local potential, it scales with the number of bands that you have to operate on, but you replace the number of plane waves with an FFT. And an FFT is at least an order of magnitude more expensive than the number of plane waves. And then you have also to multiply by the number of K points, the number of Q points in the Brillouin zone. So if you have a molecule and Q in an isolated system, NQ may be equal to 1, but if you have a solid, then NQ, the number of points in the K point grid that you have to summon, is maybe large, and then this is multiply the cost of the calculation. So this is why there have been various other ways to I mean, there have been a lot of effort to make the speed up the calculation. There is a method which is called adaptive ACE, adaptive. I don't remember what is the acronym, but okay. So you kind of make a kind of Kleiman-Villander approximation for the Fock operator, and then you can speed up certain part of the calculations, but still you need every now and then you need to calculate the true Fock operator, and the true Fock operator has a very bad scaling. So it's there is work done to make the hybrid calculation more efficient, but one has to expect some big cost if you want to use these orbitals, these schemes. Yeah, a factor of 10 or even 100 slower than a simple calculation. LDA plus U is an alternative that is more model-like. So it's a kind of trick in which you try to exploit the fact that you expect when certain elements are involved that features that are present in the atom persist in the solid. And the model we have in mind is this Hubbard model. What is the idea? The idea is that you can write or approximate the exact functional as a simple functional, could be LDA, could be GGA. Let's say this is kind of, nowadays it is more like PDE, but LDA, let's say. So you have a DFT functional, and then you add a correction. This correction should represent, let's say, is designed to represent to correct for the error that you expect the exchanging, to correct for the self-interaction error that you expect to make in the system. And this correction has typically this form, or not typically, but the simplest form that you can introduce is to describe this correction term as a coefficient, a self-interaction correction coefficient U, that multiply an occupation matrix of a particular atom over a particular set of orbitals for a particular set, for a particular spin component. N is this projection matrix, and it is n times 1 minus n. If you diagonalize this matrix, this is a symmetric matrix, so you can diagonalize this matrix. This is basically equal to U divided by 1/2, sum over all these eigenvalues that are the occupation of this occupation matrix of lambda times 1 minus lambda. Lambda times 1 minus lambda is nothing but a parabola. The higher is the value at the center of the parabola, the higher is U. And so is a term in the energy that tends to favor that the occupation lambda, the occupation of these orbitals tends to be either 0 or 1. The system is a fractional occupation of the system are discouraged. If U is very large, you pay a cost, a large cost, if lambda is not 0 or 1. So this is the essence of the LDA plus U or DFT plus U trick, of the DFT plus U functional. And the justification of this form is the fact that if you look at the isolated atom and you think of calculating the energy of the atom as a function of the number of electrons, you can actually make a generalization of the functional to fractional number of electrons. And for isolated systems, what one can show theoretically is that the energy should be piecewise linear. The energy should be piecewise linear, and should be the slope of the energy of this piecewise function should be equal to the ionization energy or the electron affinity of the negative ions. And so the slope of this energy curve, so the energy curve should be piecewise linear, and the slope should be related to the ionization energy or electron affinity. And across when you pass across an integer number, you have a discontinuity in the derivative, which is because the electron affinity and the ionization energy for an atom or for any system is discontinuous across integer numbers. But if you assume that the LDA, GGA, your approximate functional, actually instead has a smooth dependence on the occupation, and you say that instead the true thing is piecewise linear, then you can see that the correction that you need to transform the approximate functional to the correct exact functional has exactly the shape that we have here. Or I mean, if quadratic approximation is locally valid. And so basically what we have is that this correction correctly, I mean, this LDA plus U is correct the approximate results of LDA if it captures the curvature, the wrong curvature of the LDA GGA curve, so that it is re-establish the piecewise linear term in the energy, piecewise linear behavior of the energy as a function of the occupation. This is something that for isolated atoms we can do easily, because for isolated atom we can do the calculation with n, we can do the calculation with n plus 1, and then say I assume that in between it is piecewise linear. I never calculate the isolated atom with a fractional or with a fractional number of electrons. But if I were doing, I would get the smooth black curve, and it will be wrong. But I don't need to do that. I can compare n and n plus 1 directly in the isolated atom. But when I am in a solid, the problem is that we don't have a way to isolate the atom. We have an iron atom, for instance, and there is some electron that want to bind to the iron atom, and there is nothing that force the number of electrons around an iron atom to be integer, to be 6 or 5 or 7, and to prevent the orbitals that would that want to bind to the iron from partially occupy these orbitals. And this is what happens in the GGA calculation of iron oxide. If you add LDA plus U, you are kind of adding this penalty function that disfavor partial occupation of the orbitals that are determined self-consistency by diagonalize this occupation matrix. And if you do that and you put a proper value of U, the system actually end up to decide that one of the possible 3D orbitals of iron become totally occupied, and the other 4 become totally empty, and the system open again. So by adding this correction term and allowing the system to have a U that disfavor partial occupation, one can end up to have insulating behavior. This has happened also in Syria, which is a system in which the 4f orbitals are partially occupied. And if you do nothing, it would have partial occupation, but in a metallic state. Actually, it's a much better description and much more in agreement with experiment if you induce this LDA plus U, you add this LDA plus U correction, and you okay. Like that, so far, U is just a parameter, and this is the way many people in the literature have used this U, just play with it until you get the property that you want. There is a theory, there is a kind of idea that this U should be what correct for the wrong curvature of the LDA GGA functional, and so for isolated system, this will be just the total curvature because you want to reach a piecewise linear term. In solids, this is not totally, and so that would be the curvature of the LDA energy with respect to the occupation of the orbitals. In the solid, this is not exactly true because the atoms are not exactly isolated, and so therefore there is a kind of residual curvature that is due to the band structure, and this is something that in Matteo Coccuccioni PhD thesis some 20 years ago we analyzed, and so we have a formulation that then more recently has been transformed in a code that calculates the U parameters with linear response. But okay, I don't have time to go into this. If you are interested to see what is the idea, there is this paper by Matteo Coccuccioni and me. And there is also a more recent paper in which by Yuri Tinroff and people in Lausanne, in which these ideas were actually implemented in a linear response formulation. Okay, it is 3:30, sorry. And I basically discuss what I wanted to say about hybrids. Okay, let me steal 5 minutes from the break to say that this is one set of problems. And this is what happens when you have strongly localized orbitals that therefore, or atoms that maintain atomic-like feature in solids. Transition metal oxide, rare earths oxide. As I said, van der Waals interaction or dispersion interaction is a type of interaction, a type of correlation energy, is a correlation effect that is everywhere. It's a component of every bond, but it's particularly relevant when other components of the interaction are not dominant. And so in particular, it's very important for the binding of organic molecule, of organic crystals, is essential to describe physisorption, is what binds together graphite. So if you stack together sheets of graphene, what you get is graphite. And the binding energy of graphite is basically a van der Waals contribution. But is not direct covalent bond, but is more like a van der Waals interaction. Van der Waals is due to this fluctuating dipole-fluctuating dipole interaction. So you have fragments and a fluctuation of the density. A dipolar fluctuation on one side will induce a dipolar fluctuation on the other side, and these two will kind of oscillate, fluctuate in a correlated function, and this will end up giving a attractive contribution. And so it is truly non-local, and so it cannot be described by LDA, GGA, or even GGA, meta-GGA, because they are focusing on one single point in space. And even hybrids that are okay to describe, that include a fraction of exact exchange, are not good to describe these properties, because it's a correlation effect. So it's not an exchange effect. That is the best hybrids can do, give a better exchange, is a correlation effect. And so it's something that has to be described differently. And it's a truly non-local functional. And okay, this is the cartoon. And what one can do is to introduce a functional in which has therefore to deal with these fluctuations and extract some energy contribution from that. For instance, if you just do graphite and you perform calculation with gradient correction, so GGA, the in-plane lattice parameter is super well described, but the out-of-plane separation is totally wrong, and it has a very shallow minimum that is not what graphite is like. How do you deal with this error? Well, for a while, people just said, we don't want to do organics materials, we neglect it, and that's it. But especially after Walter Kohn got the Nobel Prize together with for chemistry for density functional theory. Actually, people started using DFT for organic materials, and so then neglecting van der Waals is definitely not the way. And so there have been a number of methods in which you try to add an ad hoc dispersion correction. There is a Grimm 2D, Grimm 2, Grimm 3, and so on and so forth. So there is there have been several generations of approximate functionals. Tkachenko-Scheffler have proposed other approximate corrections. Many-body dispersion is another more sophisticated methods, but they are all post SCF calculation in which you add an extra term to the functional, to the total energy. And this is kind of strange in the sense that van der Waals is a correlation effect, and so should be included in the exchange correlation function, not an extra term that you add a posteriori. And so there have been development in this non-local exchange operation functionals. There is I don't remember the name. Aiuto. Let me see. Okay, I will remember the name maybe later. Anyway, there are functionals that include van der Waals. VDVDF is one functional that has been then changed. I mean, there is a second version. There is a VV9, VV10, which is two versions, 2009, 2010, of a simplified functional, but is a real functionals. Or there are even one could go beyond RTFOC, beyond the FT, and calculate the correlation energy DRTA, or beyond RPA, and this should include van der Waals, but it is very, 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 very expensive. So Grimm just add extra terms and with some damping function, and has a good performance for a number of systems. Tkachenko-Scheffler has a different representation, but basically similar idea, that you add an extra term in the energy a posteriori, and they are successful. Actually, they are pretty successful, somehow inconsistent, not consistent with the idea that it should be a term in DFT. And then there are these functionals that have been developed across the years, and in which the functional is the energy, the non-local correlation energy, is written in terms of a kernel which contain explicitly 2 points. So is connecting fluctuation in 1 point, or then density properties of the system properties around 1 point, density properties around another point, and of course the distance between these 2 points. And these kernels are different for different functionals, and they basically all start from an expression in which you write the total energy as a interaction energy between local polarizability and local polarizability that decay like 1 over R6. And then this local polarizability is modeled in some way, and then depending on how you make these certain choices that you make for this local polarizability, you get the different functionals. And it is, again, successful. And it's a bit more complicated to calculate because it's a 6-dimensional integral. And so you have to be clever not to spend too much time in this. But Roman Perez Soler invented an interpolation scheme, and they propose a scheme that then has been implemented in Quantum Espresso. And so van der Waals functionals with these functionals is not particularly more expensive than, thanks to this trick, to this efficient integration, is not very much more expensive than normal DFT, traditional DFT. Different functionals have different ingredients, but basically the same general form, and it describes correctly for instance, the different energies, formation energy of alpha, beta, gamma phases of glycine, for instance. So PBE is very wrong, Rev PBE is also wrong. Both VDVDF and VDVDF combined with another another exchange functionals does have the right order of the phases and good lattice parameters and elastic constants. So again, alanine under pressure has wrong behavior when using at low pressure, when using PV or FPV, but instead get reasonable description when using these functionals. And okay, so basically it seems to be working and can be used in the function. VV10 has some complications, but okay, since I'm already over time, I just stop saying that there is a revised VV10 method that is basically just a simple change that make it in which we can, for this revised VV10, we can use the Roman-Perez-Soler trick to make the integration, and so our VV10 is actually as good as VV10 and much more efficiently calculated, and it gives reasonable results for many properties, including the phonon in graphite. And so I will stop here, just saying that depending on for many properties, LDA and GGA are just fine. For some systems where localized orbitals are relevant, one needs to do something special, either using hybrids or using LDA plus U to treat more correctly the self-interaction between electrons around the localized orbitals. If you are dealing with physics solutions or weak bonding in general, you may need to deal with van der Waals functionals, or include Grimm, or include Tkachenko-Scheffler corrections. All these are implemented in Quantum Espresso. Okay, I stop here. Sorry again for being too long.
Good afternoon, everybody, and I'm here for the last tutorial of the day. I'm Pietro Delugas from SISSA, as yesterday. So this tutorial will be about functionals, so about how to run the applications that Stefano has just shown you in the lecture before. And the first thing that you have to do is to go inside the directory of the inside the QMax directory in the virtual machine, and go in day 2. And in day 2, rerun again the daily update to update with the new add-ons that I have added in this morning to the repository with the exercises. And so okay. Here there is the update, and then after you have done this, we will run these exercises. A few of these exercises are a little bit heavy, so it's better if you run them on Barbara. So we just connect to Barbara with the SSH HPC command, as we have done before, and then on Barbara, and we go again in the QL directory, in the repository of the school, as we have done in the virtual machine. We go in day 2 again, and inside and also here we update the repository with the latest updates. So we just run daily updates again to download even here the latest updates. And after we have done this, at this moment, we are ready for running the exercises. We go inside the directory functionals, because this these exercises will be in the directory functionals. And we have 4 exercises. The first exercise is an example of how to run DFT plus U, and what is the correction in the occupations, and how wrongly computed as metal in GGA can turn in an insulator if you apply the Hubbard corrections. So we go inside the first exercise directory, exercise 1 DFT plus U. Okay. And here we have 4 files. And the first thing that we will do here is to run just a calculation with normal GGA. So let's see, this is the input. As you see, it's a normal input. We just have the normal values of the calculation. It's the pseudos are normal PBS all pseudos. Just to mention, I have uploaded these pseudos in the pseudo directory that we have on Barbara. So if you are not running the exercises on Barbara, then please download the files from here. The files are in in this location here. MT project 3 DD 23116 pseudo. They are in this directory. Just download the pseudos from there, and if you are not using Barbara for the calculations. If you are using Barbara for the calculation, everything is already ready there, and the files are there, and we will use a batch script. I have already prepared the batch scripts, and we are using the environment variable at espresso zero. When this variable is set up, this is the place where by default the code will look for the pseudo potentials, and so the code will look for the pseudo potentials there. The other thing that I have done, if you look at the two inputs of quantum of PW that are here, you will see that the pseudo-dir directory has been commented. This means that the program has not an indication in input where to look for the pseudo potentials, and we look at the default position. That is the directory that you set in the environment variable. But again, if you are not running these calculations on Barbara, then you need to take care of this. Either you download the pseudo potentials from Barbara and then put them in another place and set the espresso dir accordingly, or you just download them anywhere and you specify the location with the pseudo dir inside the input of Quantum Espresso. So we'll be running two Quantum Espresso calculations, one with SCF and one non-self-consistent. The one with the non-self-consistent calculation is just the same calculation as before. It's just not self-consistent. So you will read the charge density from the previous calculation, and we'll run the calculation with a denser dense of key points, as you can see here. And this non-self-consistent calculation is needed because after these two calculations, we will run a projected density of state calculation. It's the third executable that is run here. And this calculation will compute the projection of the bands on the atomic states, and we will use them to analyze the band structure of the system to see what is the difference when we use DFT plus U. When we are not using the Hubbard correction. So just start running the exercise without the Hubbard corrections, and so just submit the script. And the script is running. I think that it takes a few seconds here in this machine. Check when it stops. Okay, the calculation is done. So if we look at what is there, we have that all the files with the atomic projection. Okay, these are the projection without the Hubbard plus U correction. So what we do here now is just to move them, to store them in a directory. We just create a directory. We call that projections U, and then move all the files. All the files are all called co.po.pdos, and then something with the number of the atom and the atomic and the label of the atomic state where the bands are projected. We just copy all of these in this way with the star, and copy all of them in the directory. And they've just created, so projections without U. And this will now, we have no directory. Now we want to perform the same calculation with the Hubbard corrections. And so we have to change the two files. So the files that we have to change are SCO-SCF.in, the first input of Quantum Espresso, of PW, sorry. And here we have to add, the description of the parameter of the Hubbard correction that you want to add. We just add this is done in the new version of Quantum Espresso. This is done with an atomic card. Usually it was a little bit more, the input was a little bit more complicated, it was more involved, and it was a little bit more awkward to set up. This instead is now it's very simple. So we have just to add an atomic a card with an Hubbard. This is called Hubbard card. We have to specify which type of atomic projection we want to use. Usually, the most accurate one is the orthoatomic one, which is always good to use. The only problem is if your system has a lot of atoms, it may happen that the computation of the forces that scales up as the square of the number of the atoms becomes very heavy. And so in that case, it's maybe better to perform in relaxation first to use atomic, and only in the very last calculation to use orthoatomic. So we just specify which Hubbard correction we want to use. We want to use a simple U correction. We have to specify the type of atom, the atomic species on which we want to apply the correction. As we have seen, this system is an antiferromagnet. So you have two cobalts. We have a cobalt with a spin is pointing, one is pointing in the up direction, and one spin that is pointing in the down direction. And we want to apply the correction to both of these two atoms. So we have that. So first we have the atomic species, then there is a dash, and then the label of the atomic states on which we want to apply the Hubbard correction. So we just put the value of the parameter. We put here a number, the value of the parameter, which is 6.7553 electron volts. Okay, now in the next exercise, we will see how this parameter can be computed ab initio with the method that Stefano de Gironcoli showed you before. For now, we just take this number as it is. So we have that specified the same parameter, the same correction for the other cobalt-related species. So we have that. In this case, we have the cobalt 2, 3D, and then here we have 7.553. Then we need to make the same correction to the file for the. We have to make the same change in the file, in the input for the non-consistent calculation. So we go there, we open that file, and we just append the same change at the bottom of the file here. Then now we can again resubmit the same bash script as before, run barbaros.sh, that runs first the self-consistent, then non-self-consistent, and then runs the projection of the atomic states. So there's the Barbara page like this. We check if it's running. It's done, and even now we have the projections, but these projections are with the use. So we create another directory. We call it projections with you, and just move the files there as we have done before. So move mv co.pdos underscore star, so all the files that start like this, and we move them in the directory that is called, this time is called with you. It's called projections with you. So now we have a directory that is called projection without Q, and the directory is called projections without Q, one that contains the projections for the calculation with the U, and the one with the projections without the U. Just move the files there. Now we need to use a plotting utility to see what's happened, to see it visually what is happening, and so we have to use the virtual machine, because on Barbara I don't know if we have a GNU plot. So we just open another terminal. We go to the QMax directory. We go inside day2 again, we go inside functional directory again, and we go inside exercise 1 .tft plus u directory. Here we run one of the commands that Matic has set in the virtual machine that enables us to copy automatically, to synchronize automatically all the directories that have a twin in the Barbara user directory. So we just run the command. This is called rsync from HPC. This command just copies, just checks if there are files that are there, not here, and updates the two directories, syncing them. We just do like this, and as you see that now it's copying again, it's copying, okay, it's also copying all the files that have been produced during the calculation, so all the wave functions, all the charge density, but the thing that we are interested in are the atomic projections. So we have the projection with you and the projection without you that will be copied automatically. So now you have the same files in your virtual machine. And you have here a small file that is called vi plot PDOS GPU. That just plots, very simply plots the atomic projection of a cobalt up and a cobalt down, and of an oxygen, and prints them and save them in an APS file. So it's very simple. As we have two types of files, we will run this command inside the two directories. So we'll go inside the projection with you directory. Okay. Projections with you directory. We copy here the plotting script of the new plot. And here we just execute it's new plot minus p. That means just execute the command plot like this. So, and now here we have the file. If we look here to see that we have created the file. Okay, first we do the same thing in the other directory. We do the same thing in the one without you. We just copy, even here we copy the script like this. Okay, yeah, copy the file here. And once we have the file here, we run the same command as before. So it's new plot minus p pdos gp, yes, pdos new plot minus p and plot underscore pdos.gp. So we run this new plot script here again. And also here we have a file. Okay, the thing that we can do now is to rename the two files. We just rename this file co-pdos APS to co-pdos. This is without you. APS. And then we also rename the file in the other directory. It's not completely necessary, but just to avoid confusion. We do the same thing also here. So we have to move this file here. From here, we just call it pdos this. So now we have two files. Okay, now we want to see these two files. We just use the graphics utilities that are in the virtual machine. So we open the file browser. We can use we can use the links that are in the desktop. We just go here. So we are in day 2 now. We go in the directory functions like this, and we go in the exercise 1.dft.u directory. And then we go first in the directory that is called without you. And here we have a file, and we open it. And let's see what happens. Here we have the majority spin and the minority. Okay, the first thing, this line here is the Fermi level. So this is, in this case, it's a MET. Yes, it's a conductor. It should be, there is no gap. So what the GGA has computed is a system without a gap. It's a system without a gap. So there is a separation between the up channel and the majority spin and the minority spin, but this separation is not enough to open a gap. And that's why the system stays conductive. And this is due to the self-interaction, the spurious self-interaction introduced by GGA. And so what happens is here that we need to correct this one. That this system that in reality is an antiferromagnetic insulator is computed like that. So as you can see here, without the Hubbard correction, this is not an insulator. Then we just close this directory. We go upwards, and then we open the directory with you. And here we have a file, the same APS file as before. In this case, is with you. We just open it again and see the projections here. As you can see now, the separation between the majority spin and the majority spin is much larger. And there is a gap between the two. So the Hubbard correction has been able to correctly fix the fact that the separation between the two channels is completely complete. That there is the minority channel becomes completely empty, and the majority channel becomes completely occupied. And so we have fixed the self-interaction, spurious self-interaction, and we have correctly obtained an insulator, an antiferromagnetic insulator. Yes, antiferromagnetic insulator. So now we have done with this exercise, and we go back to Barbara. So we go back to Barbara. We just for clearance, we just close the other windows. So the first part of the exercise is done. Now we go to the second part of the exercise that I have called exercise 2, but it's just the second part of the exercise, or if you wish, it should be the first part of the exercise, and is the part where we show how with quantum espresso it's possible to compute the right parameter of the Hubbard correction. So for doing this, it's very simple. First one runs a calculation, a CF calculation. So, yeah. I was running the wrong executables. Okay, first one runs. First one runs an SCF calculation as before, an SCF calculation that is needed by the second application that we run, that is called HP.x, that instead takes the data from the previous one and performs a linear response calculation with which it computes the associativity of that Stefano presented before, that it's necessary for computing the Hubbard parameter. This is done in these two steps. Okay, just have a look at how the SCF calculation must be done. Okay, the SCF calculation is a plain one without Hubbard correction, but as we want that the occupations of the two channels that we want to, for which we want to compute the Hubbard correction must be printed out by the program, we need to say the program to compute these values, but without perturbing them significantly. So what we do is just to add two fake Hubbard corrections with a very small value of the U, so that this value is so small that it doesn't affect the calculation at all. But the program in performing these fake corrections, the program, what it does is to print out the occupations for the equilibrium, for the number two best calculation of the matrix of the occupation, sorry, of the occupation matrix for this orbital. And then after we have done this, we run the HP calculation. So it's even in this case, it's very simple. So we have just to run the first script like this. And just like this, run this. Check if it's running. Okay, the SCF calculation has already finished, and now it's running the HP calculation. If you have a look at the output of the SCF calculation, we will see that, I mean, it's a calculation where there's been no gap opening because the correction was very small. And the other, I mean, you can see this if you look at this mean contribution. This mean contribution is different from zero. It means that the density of states at the Fermi level is different from zero. And now, if we want to look at the output of the HP calculation, what we see is that the HP calculation first performs an SCF calculation. Okay, let's look at the output. It is so here we have that we just perform. Could you erase this? I mean, first thing, this program performs a calculation on a grid of 2 points. So it performs for different perturbations. So it computes the linear response of the I mean, what it does is just to add a small charge. It computes the charge response at different wavelengths, so at different periodicities. This is because we are studying a screening of a periodic material. So the screening so the screening is different depending on what is the periodicity with which we apply this correction. We can apply it to one atom and then just isolated, and it's a kind of response. We can apply it to atoms that are second neighbors, and it's another type of response. We can apply to atoms that are third neighbors, and it's a different response. And unless they are far enough that they don't interact anymore, we have to take into account all of those responses. And if we use a mesh of 444, it means that we are expecting that that the influence it's up to the fourth neighbor. It's up to the fourth cell. So here it's running on 4 cells like this. This is specified in the input of the application in this way, where we specify that we have NQ1 equal to sorry, it's up to the second node. We specify it like this. We just specify with NQ1 equal to NQ2 equal to. So the larger are NQ1, NQ2, NQ3, the longer is the distance at which we investigate, we check the influence of this susceptibility for atoms that are at larger distances. What you have to do when you compute what you have to do when you compute the Hubbard parameters is to check the convergence of these parameters. So you have to check that the values that you get at NQ1 equal 2 are the same that you get at NQ1 equal 4, for example, in order that you are sure that you are not neglecting a significant effect by longest distance neighbors. So now the program is very likely finished. Let's finish it. So now we have the output. So if we look at it, we have 2 outputs. First of all, we have the output of the program that we have already looked into. But most important, there is another file that is called prefix.abadparameters.dat. And if you open it, you will see that here you have the number of you have the values of the parameters you calculated. In this case, incidentally, they are obviously the same values that I have used in the previous exercise. So they are the same. A second part of the exercise is to see what happens to the lattice constant of this system if you run it with and without the Hubbard correction. So I just leave to you to compute the lattice constant without the Hubbard correction. I have already set up in the input here we have already set up here the calculation for the lattice constant with the VC lattice calculation for the lattice constant with the Hubbard correction. But what you have to do for exercise here is to run the 2 calculations, one with and one without the Hubbard correction. Just run, and this is done in the second script that we have here that just run the VC lax calculation. It's also. What we have to do is just to run this second script like this. Takes some seconds to run. Are there any questions? Anything that the other thing that you want to see is that, I mean, when if you look at the output of the calculations that you run with the Hubbard with an Hubbard correction, one important point of the output is when it prints the occupational matrix. So it prints the occupational matrix and it prints the eigenvalues of the occupational matrix. As you can see, obviously, from one iteration to the other, because we are not at the first iteration, the occupational matrix is already practically diagonal, and you have that for spin 1, all the orbitals are occupied. Instead, for spin 2, you have partial occupation. You have some partial occupation for the T2G's orbitals, while instead the EG orbitals are practically empty. This is because they are, I mean, they are not completely empty because they are hybridized with the oxygens, and also this is not completely, this number is fractional because there is also a strong hybridization with the oxygen. Otherwise, I mean, they are practically, I mean, what happens is that the majority spin is occupied and the minority spin is non-occupied. Okay. It's taking a while to come back. It's almost a convergence, but it's taking some time. So you have that. Okay, let's finish it. The calculation is just finished. So we have this calculation. Okay, just run the two calculations, one with and one without the Hubbard correction. You will see that the two lattice constants are significantly different because the system passes from one magnetic state to the other. Okay, let's now leave the VFT plus U part, and now we have two other exercises. The first exercise is an example on how to run an exercise with the hybrids. So let's just go to calculations with the hybrids. We just run a very small calculation with silicon, and with silicon, and we have here this is the input. Okay, there are not zero potentials with the hybrid function. So what you have to do is to run, is to indicate zero potentials for example, usually for PPE. Especially in this case, we are using an ambient function that is called PPE0. The other parameters that you need to indicate is some parameters that are needed for the calculation of the Fock potential. The first one is the grid of Q points on which the Fock potential is computed. By default, the Fock potential is computed with the same grid that you use for the SCF calculation, but this is very heavy. So in principle, you have to compute it on a sub-grid, on a sub-mesh of the total grid. And here, just for not make the calculation last forever, we have computed it in a very small subgrid. It's the smallest subgrid possible. That is just made by one, just made by one Q point. So we just specify like this, and Qx equal 1, and Qx equal 2, and Qx equal 3. And otherwise, you could have specified here any number that is 12, 12, 12, or I mean, you could have not specified nothing, and it would have been as you had specified 12, 12, 12. We could have specified 6, 4, or 3. I mean, the important thing is that the two grids are one submultiple of the other. The other thing that you have to specify is how you want to treat the divergent. I mean, there is a divergent term that must be approximated, and there are different techniques to do this. One is that is mostly used is the Gigi-Baldereschi one. That is the one that is used here, and so we just run the calculation like this. So it's calculation is again done with this batch script. It is very simple. If you look at the script, it's just as before, just the execution of PW, and you pass it the input. It's fine. In this case, if you look at the input, you see that you have if you look at the output, we have that Swift. I mean, the program first computes an ordinary SCF calculation. Here, we are computing an ordinary SCF calculation. And when we arrive at the end of the SCF calculation, we compute the Fock potential. We compute the Fock potential, and we do a compression of what is called an adiabatic compression, compressed evaluation of this potential, because we avoid, to use the potential, to recompute the potential in the next SCF step. I mean, the algorithm is you first do a DFT calculation. You compute the wave functions, and with this wave function, you should compute the Fock potential, and you need to redo another calculation, another SCF calculation where you add the Fock potential, and you make this calculation, and you try to converge this new calculation. And to avoid to recompute the Fock potential at each step of the SCF of the second interaction, what you do is just to compute it at the end of the first interaction. Perform this ACE operation, and so I have a compressed form of this. And without recomputing it at each step of the SCF, you just use it for the whole second self-consistency loop. When you have done with this, you have to reconverge the SCF with the Fock potential added. After you have done this, you will have a new new wave functions, and with these new wave functions, you compute a new AC expression, and with this, you repeat the CF loop. And so the calculation now is done. And one thing that is possible to do here is to run I have prepared the script, and it is called, sorry, I prepared the script, but I forgot to change the execution rights of the script. So this script is called getgap.sh. You have just to change the execution rights of the script, so in order that you can execute it like this, change mode in classics, and the script like this. Was also to change not only the rights but also to update the script. So we have to get the script. We have to open the script like this. Here you're opening a file, but the file is not called cpw.out, but it's called c_pb0.out. So you just change the name in all the places where the name of the file is. This file extracts the informations that are needed to evaluate on the grid that you are using the gap. So this is a file, this is a small script that is just needed for evaluating the gap. So we just rerun the script again with the right now name, and there is something that is not present. Some going with the file. Okay, it's not exactly working, sorry. Okay, we'll try to fix it, but now it's a little bit too late, maybe. Okay, so no. Okay, now what we have to do, sorry, I forgot. When we run it, okay, now now we try to run the exercise with 2, 2, 2 instead of 1, 1, 1. It will take much longer time. As you can see, if you double the number of the grid of the 2 points, the calculation runs much, much slower. And okay. Okay, let's wait another minute, then maybe it's better if we pass to the other exercise, otherwise it could become too late. Okay, but in any case, here the exercise is to run this calculation with different values of N1, N2, and N3, and to see how the gap changes. So the distance between the levels changes, and to verify that gap opens. But I think that's a bit long. And, let me just wait. Any questions? Anything? Let me see. I open the account. Okay, the calculation is done. Okay, now that there is a problem in the script that I didn't understand. It was working. Okay, no, okay, the script is not working, so I'll just sorry, but okay, just Okay, let's pass to the other exercises, otherwise it's going to be too late. The fourth exercise is about computing the lattice constant of the graphite. Even here, the exercise is made in two parts. The first part is to compute the lattice constant without with PB, and the second part of the exercise would be to compute the lattice constant with the van der Waals with a non-local functional that includes the capability to evaluate the van der Waals interactions. Here I just show you how to set up the use of this functional. Even here, even for this type of functionals, there are no pseudo potentials. So even here you need to use the PB pseudo potential, and then you need to use this variable input to DFT in which you specify the name of a functional, a non-local functional. We have chosen van der Waals df, which is one of the most common non-local functional, and the calculation is just run again as usually with the batch script that we've seen before. Okay. The question is just over, and as you see, it's done. And now we just rerun the calculation without the Albert with the PB functional. So we just open again the input. Sorry. You open the input, we comment the input DFT variable. We open the Barbara script and we change the name of the output. So here we have and we call it PB. Yeah. Okay, even the second calculation is finished, so we just compare the results of the two. We just first look at the one with PB. we look at the data of the final configuration, and we see that we have a lattice parameter of 4.666 and the C2A ratio of 2.6. Instead, if we look at the C.out, you see that now if we look here, you see that now the C2A ratio is of 2.8 between the two values. So, I mean, there is a difference between the two that changes the value of the lattice constant that is influenced by the fact that you are using van der Waals or not. And with this, I am done. Okay, if there are questions, comments, or anything, please.
Okay, thank you, Pietro. And also thank all of our tutors today. It was quite longer, but very full of knowledge. And I believe it was really helpful for our participants. And tomorrow, it's the last part of our course. We will meet again at 9 a.m. And I wish you a nice rest of the day again, and bye-bye tomorrow.
Bye. Thanks, and good afternoon to everybody. Bye.